Sir, very good evening, sir. A very good evening to all of you distinguished participants, dignitaries, and esteemed resource person. With profound respect, immense pleasure. 1 minute.
Fine. Go ahead. Go ahead, Dr. Naveen.
Actually, sir, one sir, 1 minute, 1 minute, sir. Okay.
Okay. Okay.
ठीक. Thank you, sir. With profound respect, immense pleasure, Dr. Naveen Kumar, Associate Professor, Department of Mechanical Engineering. A very good evening to all of you, business participants, dignitaries, and esteemed resource person. With profound respect and immense pleasure, I, Dr. Naveen Kumar, Associate Professor in Mechanical Department, extend a warm welcome to each of one you, behalf of the United College of Engineering and Research, Prayagraj, to the AICT Atal 6-day online faculty development program. We are gathered here on day 4 of this FDP on Advanced Manufacturing for Industry 4.0, integrating additive technologies and sustainable practices. This initiative, organized by the Department of Mechanical Engineering UCR, stand as a testament to our continuous endeavor towards academic excellence, capacity buildings, and the integration of emerging technologies into the teaching and research. Conducted this program under the occupancy space of the AICT Training and Learning Atal Academy adds to its prestige as a Atal Academy is committed to enhancing the professional competences of the faculty members across the nation through impactful and high quality training. First resource persons were Mukul sir. Moving ahead, it's my distinct honor to introduce the first eminent resource person for the day, Professor Mukul Shukla sir. Professor Mukul Shukla sir is a distinguished academician and presently serve as the head of Department Mechanical Engineering at Motilal Nehru National Institute of Technology, MNIT, Allahabad. He holds a PhD in mechanical engineering from prestigious Indian Institute of Technology, IIT Kanpur, and bring with him over 3 decades experience in teaching, research, and academic administration. Professor Shukla sir, research expertise span a wide spectrum of advanced domain, including metal additive manufacturing, polymer and hybrid composites, advanced material processing, and finite element-based design optimization. He had made commendable contribute to these areas with over 100 publications in reputed international journals and conferences. His research portfolio is further enriched by more than 7 patents and 2 authored books, particularly in advanced manufacturing and biological engineering. Sir, his unwavering commitment to academic excellence is evident in his leadership in department development, curriculum innovation, research infrastructure enhancement, and active promotion of industry academia collaboration. Through his religious scientific approach and innovative engineering vision, Professor Shukla sir continue to make significant contribution to the advancement of mechanical engineering at national and international levels. We are truly privileged to have Professor Shukla sir with us today, and we look forward to gaining for his profound knowledge and experience. And Shukla sir is also more than 14 PhD supervision and 1 postdoc and 50 plus MTech research scholars. Uh, Now invite our respected resource person Shukla sir for the expert talk for today's Atal FDP 6. Sir, please.
All right. Thank you, Dr. Naveen. Yeah. Am I visible and audible?
Yes, sir. Yes, sir.
Okay. Okay. Right. Good evening to you all. Let us commence the journey. It's the last but one day today in Industry 4.0 and advanced manufacturing. So I'll also begin by, as usual, starting with the slide sharing. Please allow me and confirm
Yes,
if you are able to see.
sir.
Sharing my slides. All right, just
Yes,
confirm. Dr. Naveen, are you able to
yes,
see?
yes, sir. Yes, sir. Able.
Okay, let me also double check my writing pad. Okay. All right, so let's start off 6 o'clock on a Thursday evening in India, because you have also had some foreign experts. Wonderful compliments to Team UCER.
Thank you,
So
sir.
this is the title of the talk. I'm going to center around additive manufacturing, but the concept is of topology optimization. I wonder how many of you are aware of. Many of you are definitely aware of optimization, but this is a concept which is entirely additive manufacturing based, called topology optimization. The whole idea is for making the designs lightweight. So my name, as introduced, thank you for the introduction. Dr. Naveen is Mukul Shukla. I'm currently at MNNIT in Allahabad, Uttar Pradesh, Prayagraj. So this is a brief overview of the lecture. I'm going to go a bit fast. Please pardon me, because there's plenty of content to be done. So let's start off. The whole motivation is around designs, whether you want to make them efficient, multifunctional, or lightweight. So design, and then we talk of creativity. So you see plenty of examples around you when you have a car or a SUV or a bicycle or iPhone, whatever. They are wonderful designs which motivate you to do better and better and better. So the topic is, as I said, topology optimization, and we'll adopt an approach which is finite element method based. And don't worry, it will be all clear, because my lecture is not only essentially lecture, it will be also a bit of the abacus finite element. Towards the later part, I'll go on to demonstrate using abacus finite element software. So am I visible also, Dr. Naveen? Can you see my camera on?
Yes, sir. Yes, sir.
Okay.
Yes,
All
sir.
right, so let's begin on a lighter note, because people are still joining. Have a look, gentlemen and ladies, on this. So, there's a figure of the same gentleman on the left side and another on the right side. Which of the two is more appealing to you? Keep writing. May I request, most of you are all faculty, but keep writing. It might not be very interactive, but let us be interactive at least on the chat box. So please keep writing. So you see, this gentleman has some extra weight down there, which is not expected. Or फिर जब इसने body shoddy बनाई, तो the weight was cut from here, and then more of a weight came around there where you typically expect. So it's like a structure. Basically, the body is a structure. So this whole concept of topology optimization is also centered around something like this. So this is a a quick beginning of topology optima. Basically, what it means is some redistribution of mass. So like the total weight of this gentleman might have been, say, 75, 80, whatever. But what he has done is, wherever needed, he has put the mass there. So just like an athlete or a wrestler needs mass at the right place, whereas around the belly and say the bag, you don't need unnecessary mass. So something like this. Let me give you another, lighter note. Abhi chalte hain. People are still joining. You recall this? Do you recall
Yes,
this?
Yes,
sir.
sir.
Yes, sir.
Huh.
Yes,
Yes.
sir.
So this was, you see, the very same Amir Khan in the movie called Dangal. So, so that's another anecdote. And then when one goes on to build body, you see those biceps and the shoulders and whatnot, with a toned stomach and extra fat around the thighs, etc., all toned down. This is precisely what we will do. I will show you. For example, wherever there is more stress, you need material, you will put material. But how? So that is what is topology optimization, obviously. Let's again, to bring the context into picture. I have put some celebrities who have some wonderful bodies here. Like these are all familiar faces named, and many of you tend to follow them also. So this gentleman, and for the benefit of the boys majority present here, I have put a lady. You know her also. Huh? Do you know her?
Yes, sir.
Okay. So what I mean to say, these are some celebrities. Let me put another example. Do you know this gentleman?
Yes, sir.
All right, he is with the Jamwal, one of the ultimate body wala. So what I am trying to simply say is this is the redistribution of the mass. So we will see precisely this. So let's begin with what is topology optimization all about. So let us say in the beginning you have a structure, a heavy structure like this, which is CNC machine. What I will do is I'll start off with this material or loaded block and take away all the extra material. So extra material from which region? Wherever there is less stress. As you know, material is provided for bearing or encountering or resisting stress. So wherever more stress, more material, less stress, less material. So what will happen is I will do finite element analysis, which is a stress analysis technique, and find the stresses. So in this area, you will find that the stresses were low. So therefore, that material has been taken off. Let me give you another analogy. Very simple, which I tell in the class also. You have, all of us have these arms, two arms. Right? These are like cantilever beam. Now, cantilever beam is fixed or supported here and loaded here. But you see the cross section, this cross section is an increasing. And as you know, the maximum bending moment is at the supports. Am I right? The maximum bending moment is at the support. Am I right? If I draw the bending moment diagram, this is going to be, if it's a point load, it's going to be W into L, where L is this. Yes. Likewise, so what I'm trying to say is, this is God created. Bhagwan ji ne aisa banaya hai aapko. Kahan par? For example, your thighs are more fat out there, heavy out there. But as you go down, they are thin. Why? Likewise, if you take a tree, the tree is more thicker at the bottom, because all the load resistance is to be borne at the ground level, and therefore as it goes up, and then finally as the leaves, they go less and less. This is precisely topology optimization. So one more example I put here. Now let's begin with design. What is the design? Basically all of us know design, but when I ask people or my students to define design, they are somehow not able to. The logic behind design is find the material, find the size or what we call dimension, or find the form or shape. For what? For any given need. So whether it is to resist torque or whether it is to resist bending, it all depends on the need. And when we say how do you decide that your need is met, is when you have that factor of safety met, and that factor of safety is nothing but safety. So your job is done successfully or safely, whatever is the job. For that job, you have to find material, whether the material is paper or mild steel or aluminum or concrete. Choice is yours. Size is, say, radius, height, length, width, etc. And shape, whether it will be circular shape or an angle shape. So this is in fact design. And also please remember, your cost of the design has to be low, but sometimes the designs can be very expensive, so those are futile. Now design today is all human centric, user based. So simple example, best example is your iPhone initially was meant only to talk. Phone, not iPhone. Phone was meant to only chat or talk, just your audio. But now today is the modern day phone is like all in one. It does calculator and photo and whatnot. I know less than you people. So ultimately, the design has to be creative. Otherwise, it will not survive in the market. You see this Apple versus Samsung. Always there is the fight for creative design. And then we also talk of safety. For example, the battery should not blow. It has to be green and recycling. So this is the concept of Industry 5.0 and even Industry 6.0 की बात हो रही है आजकल, जिसमें recyclability या circular economy. I'm sure you are aware of this, and couple of lectures have been already delivered. And please remember, design has to be economical. Otherwise, it is all waste. And therefore, we use what is called this AI ML based designs nowadays. I'm sure you have also heard of this word, generative design. I'll briefly cover in the later part. Now let's see quickly applications. Again, but for the most common examples which you see around are automotive. Whether it's a two-wheeler from Ola or Ather, or a four-wheeler from Mahindra, or the Audis and BMWs and all. Brilliant design. The exteriors are super good. I'm going to show you quickly at least 10 or 15 different examples. Now, furniture, mobile phone, gadgets. When in COVID, if you remember, we had masks. Now, masks initially were just like a cloth, but designer masks started coming. So that was the creative part, and where you go for buildings, when you see a beautiful flat or a building, you are impressed, etc., etc. Let's go ahead. So these are some quick snapshots, just to please focus on the geometry part, the design part, the creativity part, the use of material, the optimization of it. So some buildings are shown here. That's your green building here, where your AC load and light loads can be minimized. Wonderful, exciting area to research on. You see these aircrafts cannot carry any dead load. You want them to be lightweight as possible. So our light combat aircraft, or what we call it as Tejas, इसमें नाम में ही लिखा हुआ light है. It's a combat aircraft. It has to go fast at the enemy. So therefore you make it light, and therefore you use these carbon composites. And this is a Sukhoi. That black color is nothing but you see, have a look at the design part of it. These are those stealth aircraft, जो टोही विमान होते हैं, जो नहीं जिनको पकड़ पाता है रेडार, ये वो है. And you see that bat like चमगादड़ के जैसा shape है. Okay, and likewise you see beautiful shape of these Sukhois. Zero helicopter. This is going to be a future. Many startups are working in the field of what is called, because traffic is a big problem. Now, if I want to fly from say MNNIT to UCAR, why not take a flight instead of getting stuck on the bridge and the traffic? So this is going to be the future concept. Lightweight, one person or two person sitting on this helicopter for 40 miles, 100 miles, going from Prayagraj to say Kanpur or Lucknow. And similarly, you see this cars, beautiful examples, all topology motivated, all lattice motivated, all generative design motivated. So I'm not going to stick more, but you have a look at the designs and those Ferraris and some beautiful motorcycles. This is just to motivate you for thinking differently. Any of these, for example, these cantilever beam designs, if you will see the seat design, they like a cantilever beam. So you have maximum weight sitting out there, the back person, and yet it is safe to run. And there you have all your carbon fiber composites there and there. Similarly, few more examples of motorcycles, because many of you are youngsters here in the crowd. That's another motorcycle, another, and there an Audi motorcycle. Wooden bicycles. You see, you go to Netherlands, you see the CEOs and CTOs of different companies, even the president, prime minister of that country, ride bicycles. And you see, this is like a material. I said design. And design, one of the aspects is material. Now, this is wood, but you see the cross section. This is not circular cross section. This is like a rectangular, and if I take a cut, you can get. So that is just like a small project which people can do. And even in India, this was by a gentleman in Tamil Nadu. He went on to make a wooden bicycle, a bendy bike, for example. Now, if you want to travel in train and take this bicycle, there should be an option of bending it and making it half-sized, and so on. So CAD wise, you can explore all these. Let me quickly show you this just to motivate you further. I'm sure you have seen this Google self-driving bicycle. This is from Google. Let me just show you. So this is not AI. This is not AI video, old video. Right. Let's skip it.
तुमसे मेरी शादी हो रहा है, तुम्हारे परिवार वालों की गलती है, मेरी नहीं.
Now you see, this was world's first self-balancing e-scooter showcased at Auto Expo in 23 by Liger Mobility. What happens is majority of our accidents in a two-wheeler happen because of skidding or maybe losing balance. All right. So why can't we have? So this is all that creativity stuff demonstrated in Delhi. Few is back. All right. So let's proceed. Now, Vande Bharat, for example, is all using drones are using all these carbon glass fibers. So it's all design motivated. Have a look at this. This lady is using an iron board for ironing clothes. But the same board can be having a mirror at the back. So once you iron your clothes, you quickly drape them and wear them and see this. So this concept is called multifunctionality. So multifunctionality is nowadays a big thing in design concept. So let's move on to manufacturing, because I'm ultimately going to cover additive manufacturing. Now, people are talking of industry 4.0 already, and Indian industry is slowly waking. I was recently at HAL in Bangalore and, LCA division, but they have still not adopted. So majority, I was speaking to one of the other nanny industry based expert as to are they using. So they said no. However, the world is advancing very fast. People are even talking of industry 5.0 and 6.0. I don't know how many of you are aware. I have a couple of slides to cover just to tell. Now, please remember the modern 5.0 and 6.0 again are human based, and therefore it has to be flexible. And one of the subsets which is used is 3D printing, all of us know, but people are already talking of 4D printing and 5D printing. So may I request all of you to just at least catch up some terms for knowledge sake. Rest all is all known to you. So as I said, we are using generative AI, even quantum computing. Quantum computing is industry 6.0, quantum computing and neural interfaces. So it's basically all about not simply automation. Industry 4.0 or 5.0, not just automation, the human element. Remember Corona, many jobs were lost. So ऐसे नहीं होगा कि आप jobs छोड़वा देंगे लोगों की. You have to accommodate those people, those workers within the industry. So that's the fourth generation. Please remember cyber physical systems. All your machine to design office to the supply chain are all linked by internet. So that is the commonality. Quickly covering industry 4.0 elements. You see, systems are integrated over the web. IoT is used, cloud. The servers are no more sitting on your desktop. They are over the cloud. Robots, autonomous robots, big data. Data is like wealth today. Loads and loads of data is getting generated, and that is where one of the elements is sitting, additive manufacturing, which I am going to talk of. More details are already known to you. You may please see. Smart factory robotics with additive manufacturing. Industry 5.0, as I said, after COVID. So this is human-centered. So I have put a quick difference between industry 4.0 and 5.0. Let's see, for example, how many of you are aware of this word called digital twins or cobots? Please write, keep writing in the chat box. I want the chat box to be flooded. Naveen ji, Rakesh ji.
Yes, sir. Yes, sir.
अरे कुछ लिख रहे हैं गुरुजन लोग.
जी जी जी.
अरे लिखवाइए भाई, वरना फिर आप लोग when we go to the class, we expect the students to interact and speak and be lively. And we very own teachers, no matter whether you are on the mobile. See. Okay. Yeah, please keep writing. What I was saying was this circular economy and waste reduction. So you cannot have a technology which is going to pollute your Ganges or pollute Yamuna. No, not allowed. So industry 5.0, if the company in Naini is going to adopt industry 5.0, they just cannot pollute Ganges. And likewise, for example, modular production is always out there. The use of AI. So I'm differentiating 4.0 with 5.0, and 6.0 may more and more of this sustainability issues and environmental standards are being enforced on the industry. So moving on to the topic, which is all around lightweighting. So we all love those type of toned and lightweight products. For example, you take helmet. Nowadays, the modern helmets which even the cricketers use are all super lightweight. You don't and a soldier who is sitting on the border is wearing a helmet which is to be used say for 6 hours or 8 hours, wants to make it lightweight possible. So whether the bulletproof jacket or the shoe or the armor, all have to be made lighter and lighter. So whether it is a shoe, the modern day shoes, the Nikes and Reeboks are all super light. वो बाटा का heavy वाला जूता खत्म हो गया साहब, जो टूटता नहीं था. Okay, and laptops and suitcases. So those are examples. Now, when we talk of structural optimization, there are three parts. One of them is called size optimization. So the second is shape, and the third is topology. And this is going to be the talk today. As you know, size, for example, rectangle whose length is there and say height is there. And I change the L to L1 and H to H1. It is a new size. So it is an optimized size. Likewise, in shape, this is a rectangle and it is made to a ellipse types. So this is what we do. For example, I mentioned a T beam, if it is converted to a L beam or a I beam, is nothing but change in shape. But we are talking about topology optimization. And topology optimization, what happens is, I'll show you, for example, here. Are you able to see my example here, artifact? ये दिख रहा है क्या?
Yes, sir. Yes, sir. Yes, sir. Visible.
Yeah. So what is happening here is basically you are cutting out holes. As I said, you want to make it light. Wherever more stress, more material, less stress, take out material. How? By cutting out. So what has been, this is an example of an anvil. This is an example of an anvil which is used in the blacksmithy shop, in the workshop. So you see, this is a dead area. I don't want extra material unnecessarily. And please remember, functionality should not be compromised. Analogy, कि अगर आप if you are reducing your weight and dieting कर रहे हो और बिस्तर पे पड़े हो कि सर अब बिल्कुल हिम्मत नहीं है, तो ऐसा नहीं अलाउड है. So you have to be equally strong, you have to be more agile, you have to be more efficient. So likewise here also, the functionality of this anvil, when I will put for metal forming or for shaping, when I will put it here and hammer it with a sledgehammer, it should not break. So this is that example of topology optimization, making holes, cutting out holes. So please focus on the holes. I'll show you later on also. Example of a lightweight chair. You see, you start off with this, and as you know, optimization is iterative. We all have studied optimization in, say, operations research, whether it was your linear programming or assignment problem or transportation problem. If you remember, we used to do like first iteration, then we do second, then we do third, and then stop somewhere when it converges. So likewise here also, this is my initial chair, which is heavy. Now what I'll do is I'll start taking out material, I'm biting out material from which area? The area which has less stress. I give you the analogy of my arm. Likewise. So you see that this is all under stressed material I'll take out, and next iteration and next and next. So you end up with a sleek design, wonderful design like this. And please remember, as I said, functionality. For example, this person who is sitting here safely, maybe the factor of safety of this was 7. It comes down to 5, then 4, then 3, and there's a 2.6. So this factor of safety 2.5 से ऊपर होना चाहिए था. The same gentleman who will come and sit here, it will not break. This is the objective of topology optimization. A chair like this, a table and chair like this. For example, chassis. We all see chassis in all automotives, all e-rickshaw and wherever. But you can have those type of cutouts to make it a lightweight chassis. And any lightweight chassis will give more mileage. So this is the motivation of the talk in additive manufacturing. I'm going to tell you why. So those are some examples. Now, one thing you might have observed is from this or this, that the designs, the shapes are getting pretty complex. So let's see, for example, one more application is, this is aircraft. Many of you might have traveled by air. You see, this is like that wing. So you have one wing on the one side and you have another, it should be like this. So one wing is there and there is your fuselage and the other wing is there. Is wing ko, it's like a skin basically. You see this is called skin somewhere here. Yes, skin is written. So the exterior which you see is a composite skin. All right, but skins are not rigid or they are not stiff enough. So इनके अंदर क्या करते हैं हम ऐसे ribs लगाते हैं. You see like them. And then material is cut out. You see those holes. So this is that example of an aircraft wing rib. And you initially have a solid. Initially what you will have is all solid, full. What you will then start is taking out material and iteratively, first iteration, second iteration, third, fourth, fifth, sixth. So you will end up with a very light rib. And please remember, जो काम उसका है, stiffness provide to the wing will not be compromised. So now let's move on to the nitty-gritty, the exact. I'm not going to tell you the mathematics. There's a lot of mathematics behind it. Please remember, as I said, this is finite element based. So many of you might be aware of finite element. So at the back of it, the heart of it is all finite element based concept. So please remember now, what is optimization? Many of you do know it. For example, there is any function which has to be either maximized or minimized. So actually optimization in real life, we do what is called that जुगाड़. वो जुगाड़ हम लोग अपने दिमाग से या अपने अगल बगल से सीखते हैं, right? But in strict terms, in mathematical terms, it's going to be a systematic method. For example, you have studied differential calculus. याद आ रहा होगा differential calculus में you find differential calculus, you find the first derivative, equate it to zero, find the second derivative, the sign, whether it's a plus or a minus, gives you the minima, isn't it? याद आ रहा होगा. So it's like a systematic process. And there is a constraint also. Let me demonstrate this by means of an example. What is optimization all about? For the benefit of the entire. How many participants, Dr. Naveen? I can't see here. How many participants as of now?
More than 81, sir.
Okay, brilliant. Thank you. Thank you everyone so much. You know, it's 6:30 evening on a Thursday, very challenging time. But nevertheless, let's make full use of the time. Yes, so I'll tell you a design problem, design optimization of a Coke can. We all know what's a Coke can about. What is the problem? The problem is the volume of this is 300 ml, which we normally use for drinking. And it is made of an aluminum alloy sheet like that. Okay. Now I want to make, whose cost is given, say 2,500 rupees per square meter. I want to minimize the cost of it. So the cost of making this can has to be minimized. So let me demonstrate how it is. So either I can, as you know, in a cylinder, you have two variables, radius and height. So here the height is more, the radius is less. Versus this on the right side, the height is less and the radius is more. Please remember, volume has to be constant, 350 ml or 1 liter bottle or 2 liter bottle. It is constant. So let's solve it. So as I said, constraint is a volume, pi r square h. It's a cylinder. Pi r square h is equal to 350. So h will become 350 upon pi r square. Why I'm doing this is because I want to convert two variables. Two variables, what? Radius and height. I want to convert it to a single variable problem by substituting it. And then my objective function, as I told you, is like a sheet metal. You have to rotate it like this. I mean, bend it like this and use it like a cylinder. So this is the surface area of a cylinder. 2 pi rh for the curved surface, pi r square on top, pi r square at the bottom. So pi r square plus pi r square is 2 pi r square and 2 pi rh. So that is my surface area. What is my objective? My objective is to minimize the surface area. What is my constraint? The constraint is volume. 350 ml cold drink आनी चाहिए उसमें Coke can में. All right. So let's solve it. As you know, this is now converted into a single variable. Put this here, it will become in single variable in R. Now what I'll do is classically I will differentiate the surface area with respect to radius, equate it to 0. I will get a radius as equal to 3.8. Roughly जो आप हाथ में पकड़ सकें, इसका diameter कितना आ रहा है? 7-8 सेंटीमीटर आ रहा है, जिसको आप आसानी से पकड़ सकते हैं. But when you plug it back, you will find that the dia and the height are equal. So neither is your design like this. See, backside, what did I say? Neither it will be like this, nor it will be like this. You will in fact get a square shaped can whose height h is equal to dia. So this is that simple optimization exercise which I am trying to showcase. Why? Because in topology optimization also we will use constraint. We'll have an objective function. We will have variables. We will not do this differentiation, etc. Instead, we will use finite element method. Is it fine so far, Dr. Naveen? Any comments?
Yes, sir. Fine.
All right. Okay. Right. Let's move on now. When we talk of optimizing, what do we want to maximize? जैसे हम चाहते हैं कि हमारी दौलत बढ़ जाए, हमारा प्रॉफिट बढ़ जाए, हमारा नाम शोहरत बढ़ जाए. ये देखिए, ये सब लिखा हुआ है. इनको हम बढ़ाना चाहते हैं. And likewise, few things which we want to minimize. For example, the investment, the loss, the factor of safety, delay, friction, vibration, noise. These are all parameters which we want to minimize. On the left, you have maximize in But in topology optimization, what do we want to maximize or minimize? Let's see it. Now in topology optimization, I want to minimize stiffness. Stiffness, as you know, is K, which is given by load per unit deflection. So I want to, load is constant. I want to maximize the stiff. It means it should not deflect too much. It means, what it means is, it means that my deflection has to be minimized. So that is their deflection minimum. It's written here. I want to minimize my deflection. इसको दूसरा word बोलते हैं, stiffness का उल्टा होता है compliance. So you want to minimize compliance, maximize stiffness. However, we will use the strain energy. Strain energy is the energy under the stress strain diagram, and strain is nothing but deflection. So we want to minimize strain energy. We want to minimize deflection in topology optimization. So I hope you recall this. This is what we will do. I hope you also recall this for the benefit of all those of you who joined late, because I can see the ting, 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 ting coming. It means people are still joining. Okay. Right. So what are we trying to do is make it lightweight. Why? Because it will become multifunctional, cost will reduce, manufacturing will become smart. Now, the obvious question is, how can you make anything lightweight? So whether it is a table or a car or an aircraft, इसको हल्का कैसे बनाएं भाई? तो उसके कई तरीके हो सकते हैं. Let's see. For example, the simplest solution is change the material whose density is low. So instead of mild steel, let me start using aluminum. But as you know, when the strength, this is density. But as you know, the strength of aluminum is less than the strength of mild steel. So when the strength reduces, the size has to be increased. So what I'm trying to say is you can make a chair or a bridge of paper also. All right, but the strength of paper is less. Because the strength of paper is less, the size of paper which you will use to make a chair will be big. So now this is the trade-off. What do we want to use? Whether we change material or we use a high strength material or a low density material, how to change the size, how to even vary the shape. This all together is the lightweighting concept. And the final thing which is used in topology, and that is what I have written here at the bottom, reduce material from where? जहां पे नहीं चाहिए वहां से हटाओ ना भाई. So in organizations also, there are a lot of overheads, unnecessary dummy expenses. उनको हटाइए. जहां पे बढ़िया काम हो रहा है उनको प्रमोट करिए, और जहां पे गड़बड़ काम हो रहा है उसको हटाइए. ये लाइफ की फिलॉसफी, and this is topology optimization philosophy. Let's see now. Let's going slowly into topology. Now, as I said, I want stiffness to be maximized. I want deflection to be minimized. So let me tell you a simple example of a cantilever beam like this. Now I am dividing it into a 5x2 grid. So I have 5 columns and 2 rows. So it makes it 10 cells, isn't it? 5x2, 10 cells. But I am only allowing you to place 7 cells. Don't worry, it will be clear in the immediate half a minute. I am only giving you 7 cells. What it means is 10 cells is equal to 100% weight, and 7 cells means 70%. So I am reducing my 100% to 70%. But how? Placing the cells wherever you want. So let me start off. When I have 10 cells, I'll have 100% volume, something like this. See this? Now, when I say reduce the volume or reduce the mass by 30%, from 100, bring it down to 70. So it means instead of 10 cells, I will give you only 7 cells. But the choice you have as a designer is put it in any location, the way you want to locate it. So let me show you. For example, I put 2 on the top and 5 on the bottom. This is one structure. I put 5 on top, 2 on the bottom. This is another structure. So now if I put a point load at there and fix it there roughly, same fixing again here, same point load here, the deflection of this is different, the deflection of this is different. So likewise, placing the material at different places will give you different structure, and when you load it, you will get different stress. So redistribution of mass, redistribution of stress is nothing but topology optimization. Like another example, I can put 3 on top, 4 on bottom, 4 on top, 3 on bottom. So actually, like I can have a fancy shape like this also and put the point load there, fix it here. But what it means is I'll have actually 10 C7, making 120 possible designs I can make. हर एक का deflection अलग आएगा. लेकिन इनमें से हमको क्या करना चाहिए? I want a deflection which is minimum deflection. So I will pick out of the 120, out of these 120 possible shapes, I'll pick the one which is most stiff. Are you getting? I hope समझ में आ रहा है क्या है topology optimization. I'll just clean this slate. Yeah. Are you
Yes,
getting
sir.
it? हाँ, किसी
Yes,
ने
sir.
ये beam तो not allowed because this is 100. I only want 70%. So one of you makes this beam, the other makes this beam, the third makes this. So 120 participants are there. सबने अपनी अपनी beam की डिजाइन करी, उस पे वही लोड लगाया, वही फिक्स किया. तो what you will find is see delta 1 से लेके delta 120 तक. But one of them, say number 75 is coming out to be the stiffest. So that is what we have to check for. फॉर एग्जाम्पल एक दो चीजें नॉट अलाउड हैं. देखिए ये ऐसे अगर हवा में हो गया ये, सो दिस इज लाइक से वेस्ट एंड दिस इज ईस्ट, नॉट कनेक्टेड, ये नहीं अलाउड है. एंड सिमिलरली पॉइंट कॉन्टैक्ट इज ऑल्सो नॉट अलाउड, पॉइंट कॉन्टैक्ट इन टोपोलॉजी ऑप्टिमाइजेशन. तो प्लीज रिमेंबर, एज आई सेड, होल्स हम करेंगे, होल्स बनाएंगे. दीज आर होल्स, दीज आर होल्स आई एम क्लेमिंग. तो आवर शेप, आवर फोकस इज ऑन द कनेक्टिविटी, नॉट ऑन द शेप. So this is one of the most commonly seen examples of additive manufacturing. So actually, if you see, let us say, I take this as a solid. So this is a full solid. Now what I'll do is start cutting it out. As you know, the stiffest structure would be the one which has full material. But no, I want to make it lightweight also. So you see, these are holes. So my focus is basically on the holes, number of holes, location of holes, and size of holes. Have a look, ladies and gentlemen. You see, इस होल H1 का साइज अलग है, इसकी लोकेशन अलग है. H2 का साइज अलग है, लोकेशन अलग है. So the way in the structure, the way you cut out is going to give you another geometry. अभी मैंने आपको example दिया on a beam, 120 possible components. So different topology. This is the meaning of topology. At least all of you should understand what is the meaning of topology. The meaning of topology is basically around connectivity. So how are you connecting one area to another? Say left part is connected to the rightmost part. How? By these holes. तो कहीं से हटाया, कहीं लगाया. How do you control number of holes, number of each location of each hole, and size of each hole? Now let's see an example. These are real examples picked up from ANSYS. So using ANSYS finite element software, this is my initial design. This is a disc wheel. Initial design. It is a heavy design. I want to make it lightweight. आखिरी में देखें, आखिरी में you will see that you get a lightweight. So first thing I will do is I will do finite element analysis. Why are we doing finite element? Please tell me, why are we doing finite element? Why are we doing finite element?
To evaluate the stresses at for different points as per the requirement.
Absolutely correct. Absolutely. 10 out of 10. Yes, right answer. हमने कहा कि somewhere you have more stress, somewhere you have less stress. But how do you know it? To get a guess, to get an estimate that which of them. ऐसे थोड़ी ना कि मैंने बोल दिया कि यहाँ पे कैंटिलीवर में होता है. नहीं, you have to find it out. To find it out, we use a virtual stress analysis technique, which is based on finite element. All of you know. So what I'll do is I'll do the standard finite element using ANSYS, Abacus, plenty of software allow. So what you will see here is like a stress plot. As you know, the blue stress means minimum. I'm sure you know it. And the red there or yellow or green are maximum. I'll also demonstrate towards the later part. So what happens is, ये नीचे का जो बीच का blue है, this is the lowest stress region. And as I said, what we'll do is first we'll do finite element. After having getting a stress trend, an idea of stress, we will do the next step is topology optimization. So what it will do is it will remove the materials from the outer rim. ये blue जो area बाहर का दिख रहा है उसमें से हटा देगा और बीच के में से it will take out all the material. Do you agree? कैसा दिख रहा है? So this is topology optimization, and we will do some cleaning and smoothing and do one more. So you see all that. Let me just clean this. So all that red area, the yellow area, the green area is all gone, and you have almost like blue everywhere. The meaning of blue is basically uniform stress. तो ऐसा नहीं कि दिमाग में बहुत स्ट्रेस है और हाथ में स्ट्रेस नहीं है। अगर शरीर का स्ट्रेस टोपोलॉजी ऑप्टिमाइजेशन करनी है तो you have to have uniform stress. And please remember, you started off with that design and you ended up with this design. Obviously it is a much more lighter. So this is an example of a disc wheel. Let me give you another example. This is of a brake pedal. We all drive cars and all, or even motorcycles. We apply brakes with these brake pedals. Now imagine, 100% volume is there. Blue, I told you, is low stress, the sigma is low, and the green is say high. So what it will do is it will retain green. ये देखिए green को सब बचाए हुए है, लेकिन ये blue के area को सब खोद दे रहा है, खा जा रहा है. So it's biting from those areas where there is blue, less stress. And from 100% to 73 first iteration, then 64 second iteration, 59%, 50%. So I came down from 100% to 50%. Please remember, brake pedal should not brake, otherwise it is useless. तो हल्की बॉडी करी और पता लगा कि क्लास ही नहीं पे ले पा रहे हैं कि सर वो तो थक गए. बोले हम थकना नहीं है, चलते जाना है, बल्कि ज्यादा एनर्जेटिक फील करना है. सो दिस इज द ब्यूटी ऑफ टोपोलॉजी ऑप्टिमाइजेशन. योर स्ट्रक्चर्स आर गोइंग टू बी more efficient. And as you can see, what is the advantage of making, why do we want to make brake pedal light? Why do we want to make it light? कार में ब्रेक लगा रहे हैं, एक्सेलरेटर दबा रहे हैं, है ना, वो ब्रेक पेडल है, एक्सेलरेटर पेडल. व्हाई डू यू वांट टू मेक इट लाइट? What is the advantage in making it light?
We can save material.
Yeah, that's
So
fine. That's fine. But give me a more valid answer, where I'll give you a 10 out of 10. Material saving, fine. What is the advantage of a lightweight brake pedal? This is better than this. Material saving, fine, I'll take it. Why? What is the functional advantage?
Maybe less force can be applied to achieve a maximum result.
Okay. Yeah, but what I was expecting is, let us say I'm at Prayagraj and I'm going or driving to New Delhi, which is say 600 kilometers. Now, when you drive a car from Prayagraj to Delhi, at least 100 times or 200 times you will break it, isn't it? Then you will. Now, this is a mass which you are pressing it. So you want a light, it has to be a comfortable ride, comfortable drive. So that is the advantage which you get of a lightweight brake pedal. The fatigue which takes place on your body after driving for 8 hours or 10 hours continuously is less in case you have easy maneuver. Whether it is a steering, the old steerings used to do this, but nowadays the power steering and all, you just do a bit. So it creates less fatigue. So that's the beauty of a topology optimized brake pedal. I'll skip this. So those are some examples. This is a crane hook. You start off with that, and when you do topology, some shapes are getting generated. So what the problem is, so not everything is so easy. The problem is you get some very complex shapes. And please remember, as I said, design on a computer is very easy, but ultimately it has to be manufactured. So all these complex shapes ought to be manufactured. Now, I've shown you some very fancy, I'll show you a few more. Well, they're very difficult to manufacture, whether you have to use welding or you have to use casting or CNC machining. Well, it becomes very challenging. So therefore, the savior or rakshak is additive manufacturing. As you know, additive manufacturing is moldless, die-less. You don't need a mold, you don't need a die. If you can conceptualize the design, you can print it. Any complex, this is the number one advantage of additive manufacturing, that any design, howsoever complex it is, you can manufacture it. So let's see. For example, this is a classical example which is shown in the additive. You browse it, topology optimization, you will get it. You see, this is brazing here or welding done here. So they say, imagine there are 5 parts or 7 parts, but you can additively manufacture it like this. And you can see all those holes cut out there. You see, I told H1, the location of holes, the size of holes. So such complex designs are easily manufacturable by additive manufacturing. Conventional welding, CNC, or a hybrid technique is not so feasible. So that is one of the major industry-based delays on the adoption of topology optimization. So slowly people are using, because you see, for example, this is made of, say, stainless steel. Now imagine if stainless steel is there or titanium is there, making it using 3D printing, you need a metal printer. Now, even MNNIT in Allahabad doesn't have a metal printer. So you do a brilliant design. I can do it using Abacus, but I can't manufacture it. So this is the biggest disadvantage, or not disadvantage, limitation as of now. That you come up with a good design, which is highly lightweight, functionally good, but you're not able to manufacture. And as you know, as you also know, additive manufacturing is a batch process. You can't get, say, thousands of products out of additive manufacturing, but this is the world going to be. So I'm showcasing some of the examples. You see, this is an exhaust manifold out of metal additive manufacturing, and see the complexity of this object. Another seat bracket, all these are picked up. I've given all the links, you can also see. You see that example, so free form shape, multiple holes, lightweight. This is the beauty of topology optimization. So one example which I do for students in the class, whether it is UG or PG, is this connecting rod. So this con rod, I want to make it lightweight. So you see that is the small end, then that is the big end. So we will try and make it lightweight. So let us see, slowly we are going towards that Abacus demo in the later part. The time now is already 7 o'clock. Yeah, so I have 30 minutes. I can run through. All this, please remember, ladies and gentlemen, is software based.
Sir,
You don't.
you can take 15 to 10 minutes more. No issue.
Let's see.
Yes.
Okay, we'll see to it. At least I could start on time. I'm happy. Yes.
Sir,
There's a software.
I have a question, sir.
Please. Yes. Welcome.
Sir, if we remove the excess material from the any automobile, then how can manage the stability of the structure?
You will have to do stability analysis. अभी मैंने क्या बोला कि डिजाइन तो बना दी, पता लगा मैन्युफैक्चरिंग नहीं हो रही, डिजाइन तो बना दिया, पता लगा कि उसका स्टेबिलिटी नहीं है. So you have to explore that part. As you rightly said, I remember I gave the example, मैंने दिखाया था ना, कौन सा example बताया था? Chair. So the chair had 4 legs. What if this topology optimization removes one of the legs? So for the 4-legged chair is now getting into 3 legs. तो वो तो stable ही नहीं रहेगा. So I will tell you होता क्या है, इसमें एक concept आता है, ये आएगा, ये मैं बता रहा हूँ, अभी बताऊंगा, design and non-design. So some area, for example, frequency. So what we can do is we can check for the frequency. So if you have a fancy shape, the frequency of this can match the natural frequency of this can match with the forced frequency. अब पता लगा उसमें resonance होने लगा. So these are checks which you have to. So there are plenty of checks. It's not so easy. I'll tell you a few checks in manufacturing also. But rightly said, very good question. Yeah. Any other question?
No, sir. Thank you.
Yeah, you have to do जो भी आपका downstream. What did I say? I use the generic word. I use the generic word that the functionality should not be compromised. And when you said ki what will happen to the stability, it means the functionality is getting compromised. I will not allow any compromise. For example, resonance taking place is a compromise. I will not allow. Okay, we'll see few more. So I was just covering softwares which are used for topology optimization. The leading software is, earlier it was called OptiStruct. अब इसको Altair company ने Inspire नाम दे दिया. This is a very fast. Please remember, optimization is iterative. It takes time, depending on the model. It could take 3 hours, 4 hours also. I'll demonstrate 2D examples to you very quickly. We'll solve. But SolidWorks also has it. ANSYS also has it. Abacus, Fusion 360, OptiShape. These are all the popular softwares. I'm going to demonstrate towards the end using Abacus. Now, as I said, remember that ANSYS ka brake wheel, yaad ho na? The first thing we did is static FEA. Why? To get an idea of the stress, a trend of the stress. Once you get that, then you start. Now, moving back to this example of a con rod, what I will do is I will divide it into a design area and no design area. This no design ko we also call it as freeze. What is the meaning of freeze? Freeze means don't disturb. As you know, this is a connecting rod. This is connected like this. So what I will do is I will demarcate this big end. ये जो इधर का दिख रहा है, ये small end है, इसको हम छेड़ेंगे नहीं. I will not disturb it. So I will call it as non-design area or frozen area. However, this middle portion which you see, this middle portion here, I will eat out material. So I will make it lightweight, but from which area? From this central area. So you have to have some idea of your problem. As I gave the example is the four legs. So those legs will be made tapered, but they have to be there. At least 4 legs have to be there. So you have to design into, you have to divide your partition, your model into design and non-design. And this will be clear in the later slides also. So let's now go towards the abacus optimization, how you do it. Please remember, Coke can ka example yaad aa raha hoga. So that's what we will do. We will do topology optimization. Shape and size we are not doing, although it is possible. We will have variables. So like radius and height was a variable where in the Coke can problem. Similarly, we will have here what is called volume fraction, or basically mass. Volume fraction, you will begin with 100 and say come down to 60. It means 40% we will reduce. So volume fraction is the first variable, and strain energy, as I said. Strain energy is another variable. These are the 2 variables. What is the objective? The objective is strain energy to be minimized. So this will be our objective. And what will be our constraint? Our constraint will be volume fraction. Say volume fraction is now 60. Keep it at 60. 60 ke niche nahi jana. Otherwise, if you keep, see, volume fraction is there 60. If you allow it to go down, 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 it will try and bring it down to 0, and there will be no strength left. So therefore, this is the definition of it, which I will be showing you. And there is also sometimes some geometric restriction, which I will cover towards the later part. Now, this is the first example picked up from that YouTube video from Abacus. This is like a bridge. जो आपका bridge है नैनी वाला देखा होगा आपने. So what I will do is from here there are cars going from Prayagraj towards Naini. Okay, but this is that initial shape. So I will do, what is my objective is minimize deflection for a 30% volume constraint. So what it will happen is start from 100 and decrease by 70 and come down to 30. You will just now see brilliant. I also have it. I'll show you. Now, first thing you need to do is design or no freeze area. This yellow area which you see is where from you will take out material. बट ये ग्रीन वाला जो है इसको हमने नॉन डिजाइन रखा है इसलिए क्योंकि यहाँ गड्ढे गड्ढे अगर आप सड़क पे बना देंगे तो कार कैसे चलेगी. So that bottom area, isn't it, on which the cars will run or the lorries will run, that I have kept non-design. Don't shadow it. Which one? The green area at the bottom. However, you are free to play with this area. What I'll do is the first step I will do, as you all know by now, is first step is do static FEA. Why? Because you will get an idea of the stress. The output will be the von Mises stress. You will get a trend. Now, as you know, see this blue is the minimum stress. ये देखिए यहाँ पे stress है ही नहीं, यहाँ पे stress है ही नहीं. Okay, and you know this is like a simply supported beam. You see this? This is supported here. Bridge है ये, bridge का ऐसे supports है यहाँ पे. So the maximum stress is coming at that red yellow area. So this is like a beam like this. So this is your bridge there, which is supported here at those. A bit of an overhang is also there. And you can see the maximum stress is e to the power 2 and the minimum stress is virtually 0. So no stress here, load is not there. Plus, please remember, as I said, the niche wala area is a non-design. So what happens is you get a trend. What do you get? A trend is like, see, you need material from this से लेके यहाँ तक material रखेंगे. इस material को सब हटाओ. ये नीला नीला जितना है ये सब हटाओ. So you will start with 100 and go down to 30. So this is the end result. The link is given there. You can see it's a 35 odd minute video. So how did we start off? We started off with a block like that, a heavy block like that. So this was that non-design area. ये जो नीचे का सड़क वाला area. So you can see there are no cutouts here, no holes here. The road is nice and good, but all that is the cutout, all topology. All this area is all eaten up. all this area. So your 100% becomes 30% over a period of time. Is it clear, guys?
Yes, sir. Yes, sir. It is clear.
Okay. Yeah. So this is a 3D example I gave you. I'll show you another example. This is a simpler example of a bracket. Like a bracket is there. I'll demonstrate this. Two examples I'll demonstrate. So this I'll demonstrate. So now this is like a bracket which is fixed on the left end. You see, this is fixed in a way. And I'm having load, like a pressure load on the top here. Okay. What is the objective? The objective is to minimize the strain energy, meaning minimize deflection. What is the constraint? The constraint is 60% volume. So you are bringing it down from 100 to 60. It means 40% you are reducing. I'll show you this later on. Now, as I said, freeze, what to freeze and what not to freeze. Normally the guideline is कि जहां पे लोड लगा है, जहां पे बाउंड्री कंडीशन है, उनको नॉर्मली हम छेड़ते नहीं. ओके, इन रिमेंबर इन द चेयर वेयर यू आर सिटिंग, जहां से बैठा आदमी वहीं से अगर हटा दोगे आप तो पता लगा बैठने की जगह नहीं है. So what happens is, this is that frozen area which is load. I have not frozen the boundary condition area. So you will see when you will do first step, as I said, is do static FEA. You will get a trend of the stress, and you will see the maximum stress is on that top, and the minimum stress is on the left there, and this is the trend. So your output will come like this. See this, all this area is eaten up. All right. And now you will get something called mat property normalized. Mat property normalized is varying from 1 to literally 0. ये 1 है max, ये 0 है. 1 का meaning है nothing has been disturbed, full solid है. And 0 का meaning है हवा में है या कुछ भी नहीं बचा, सब खा गए हम यहाँ से. किससे? 0 area से. So this is the type of a plot. Let me clean it. This is the type of a plot you will get. This is not stress. Please remember, the previous slide was for stress. That is not stress. You see here, this is the von Mises. Red is max, green is next, yellow, orange, and slowly. Blue, as I said, is lowest stress. Wherever you have lowest stress, remove material. And why do we use finite element? As the name is there, finite element. तो इसमें छोटे-छोटे टुकड़े हैं. ये देखिए elements हैं. These are tetrahedral elements. You know what the topology optimization I'll demonstrate is dhire, it will go on eating or removing elements. It will go on removing elements, and that is the beauty of topology. So ultimately, you will get a lightweight structure, which is topology optimized. And please remember, the factor of safety is not violated. Okay, so yeah, like that. So here also, yes, same I told you. Now, as I said, when we do this, what happens is you start with your Conrod example. You start off with this. Now, what happens is you get some very funny shape. You know, जैसे chicken का वो टांग लग रही वैसे type का है. But ये चलेगा नहीं, ये बनेगा नहीं. What you have to do is some cleaning, and then you see those shapes are coming randomly. So what you will have to do is some sort of a alignment or a cleaning in CAD, so that it has to be manufacturable. And please also remember, I'll tell you later on, you need symmetry. For example, the front and back, the front part and the back part of this. Somebody asked me rightly, what about the stability? So manufacturability, like for example, all the manufacturing engineers know, for example, yeah, drawing direction or parting line, parting surface. So these are what are called geometric restrictions. So I'm going to cover later on. When you enforce geometric restrictions, when you enforce frequency to not match, then what happens is you get a shape which will be practical to use. ऐसा ये करेंगे, and then we will solve again. We'll do one more validation. So this was that example. So your small end, no, it's a design, non-design area. It was not disturbed, but all this central area was eaten up slowly, bite by bite. Yeah, like there you can see this area is all. So yellow is my non-design. Yellow is big and non-design. अगर आप यहाँ से काट देंगे, ये ऐसे काट देंगे, तो वो connecting rod तो fail हो जाएगी, वो काम ही की नहीं है. So please remember, do not make it non-functional. So otherwise your topology optimization is all useless. Let me quickly cover and then we'll move to the demo. Manufacturing constraints. For example, I was just talking of the drawing direction. In casting, you know, If you have to draw it out, it has to be reducing in that. But if you have some, sorry, it has to be like this. So इसको आप बाहर निकाल पाते हैं. Reducing means reducing in the opposite direction. मगर अगर ऐसा उल्टा होता है, you cannot draw it. Okay. So whether it is extrusion direction or draw direction. Likewise, for example, we talk of what is called symmetry. I just mentioned the front symmetry with the back symmetry. Sometimes you need a part, for example, like say this, over the pitch circle diameter, if you have 4 holes, they are all symmetrically placed at 90 degree, or if at 45 degree like that. अब पता लगा ऐसा आपका टोपोलॉजी ऑप्टिमाइजेशन आ गया, एक यहाँ आ गया, एक यहाँ आ गया, एक दूसरा यहाँ आ गया, तीसरा यहाँ चला गया. ऐसा अगर नॉन सिमेट्रिकल शेप बन के आया, फनी शेप, इट इज वेस्ट. The functionality will be compromised. Somebody asked about what will be the stability. So what I can do is I can enforce cylindrical restriction. I can impose symmetry. Likewise, in additive manufacturing, as you know, when the angle is more than 45 degree, this angle is more than 45 degree, you need supports. So that is what happens. So when this angle is more than 45 degrees, say like this, you will need supports here. So supports, as you know, in additive are a waste. They will eat up time, they will eat up raw material, they will add to the cost. So you want to minimize supports in additive manufacturing. So the overhang angle, isko bolte overhang angle. So I can give it ki make a shape which does not have an angle greater than 45 degree. Otherwise, your design is fine, but it is manufacturability is poor. Okay. So yeah, time is now running short. Let me skip all this. This is generative design. Time nahi hai. 7:10. I need to demonstrate also. We will talk sometime later. Generative design. Please make a note of this word called GD. As you know, Gen AI, वैसे Gen design भी आ रहा है. Yeah, so this is the most popular example of a 3D printed bracket. Normally your bracket is like that heavy, but iteratively you design and you end up with a very optimized design which can only be 3D printed or additively manufactured. It's very difficult to do CNC machining of these. As such, CNC machining is like a subtractive process. It eats up a lot of chips are wasted. So why not additively manufacture? So that additive is the, so this I'll skip all. And you will have something like this. Now the another thing. So 3 things I'm telling you today. First is topology optimization. Second is generative design. I'm not covering in detail. And the third is called lattice designs. We as engineers are familiar with material science, the lattices in material science, whether it was BCC, FCC, or hexagonic close packed, etc. Basically, there was arrangement of atoms. Arrangement of atoms in space was nothing but lattices. So here also what we do is the arrangement of material. But you see, this is like that Conrod type, like a Conrod type of a thing. Your big end, your small end, different shape. But you see, material is taken out. Similarly, here materials. So what we do is we create holes, but with different shapes. So plenty of examples I have said here. No time to cover all of them, but I wanted to cover this name of the software. This is a freely downloadable software called End Topology. End Topology. तो उससे बन क्या रहे हैं? For example, this I have an example of this on the left side here. This is actually a implant. So I wonder if you are able to see if we do it offline. I have plenty of examples, by the way, in metal and all, but obviously it becomes very difficult to show in online mode. Yes. So I was talking of this. This is nothing but a hip joint. Our hip. In our hip, you have like this. So this is that katori type of a thing, and you have a stem like this. So this hip joint is like a ball and socket joint. So this is made additively. And you will see here, this is a very rough surface. So I'm showing you some, I wonder if you are able to see. It's a very rough surface. But inside of it is a very smooth surface. You do hybrid manufacturing. You do CNC machining. So this is a smooth surface because the ball and socket, it rubs there. So you need a minimum wear and tear. So that therefore it has to be smooth. Whereas here it is made rough. Can anybody tell me why do you need a rough surface on the implants here? Yeah, my question is, why do you need rougher surfaces in implants? See this is another implant I was talking of. ये देखिए रफ कर दिया है यहाँ पे using lattices. Anybody in implant, in bio implant, whether it is for orthopedics,
To maximize the bonding strength of nearby muscles.
Bone can grow.
both
Can be done.
correct. Both answers are correct. What is called osseointegration? So this is a foreign body, you know, it's a metallic thing, and inside your bones are not metals, they are ceramics, and they are much less stronger. And this is loha lat type की चीज है, उसमें डाला है, it has to integrate. So sometimes the doctor is forced to do a second surgery, saying that the body did not accept. So that's the reason. Yes, the growth of the cells. So हड्डी जुड़नी चाहिए, or the body has to assimilate. Yes. So likewise, this is an example of a flip flop or a shoe. होता क्या है, as you know, when we walk, you know, we have different patterns. So somebody might be, थोड़ा देखा होगा जूता एक तरफ से घिस जाता है, तो जहां पे ज्यादा लोड आ रहा है वहां पे ऐसा डिजाइन करिए कि वहां से घिसे नहीं. तो होता क्या, प्रॉब्लम इज, यू नो, योर गेट पैटर्न, द वे यू वॉक, ऐसे ऐसे वॉक कर रहे हैं, that you have to capture and design your shoe sole accordingly. And please remember, ये holes कटे जो हैं, these are all lattices. All right. And topology is the software. There you can all see it. Yeah. So those are my lattice designs, etc. The example is given here. Better see here. See, I was just talking of that ball and socket. So that thing which I showed you is sitting here, and this is the inner thing. And as you know, our bones are all very porous. Now, if you want to do a bone modeling, many of you are into biomodeling and all. अब आप इसका देखेंगे, this is not a solid, ladies and gentlemen, it's not a solid. You have to model it with what is called pores. So a healthy bone will have some pores, or then when you have osteoporosis in my age, say 57, 58, 60, 65, what happens is the density of this material goes down, the pores become small, big. These are small pores, these are big pores. The strength of this, these are small pores, these are big pores. The strength of that goes down. Now, if you want to do the modeling, you will have to use lattice designs. Okay, time is a bit less. Use क्या करते हैं, ये सब use करते हैं. देखिए gyroid. So gyroid is that shape which is a TPMS, triply periodic minimal surface, and you know the fluid will go. So your bones are not through and through. If you see porosity in the bone, you can't. I think I had some example. Yeah, I have. You see, this example is a through and through hole. If you see, you can see the through and through hole. Whereas this is gyroid, you can't see through and through. It's like intertwined, ऐसे ऐसे करके जाता है, और यही पेड़ों में होता है, यही bone में होता है. So in trees, you know, the fluids are sucked from the earth and it goes to the farthest corner. How? By this gyroid structure. Wood. So wood is the best example. So yeah, time is less. So let's move to the last part. 15 minutes for me. Yes. So because I need to also tell you where are some good sources. So those are the sources. This is that book by Benshaw, which is wonderful in topology optimization terms. All the basics are given, slightly advanced, but abacus topology optimization, I remember I spoke of the bridge. You can see them there. And Conrad also I mentioned. So plenty of papers are published, but they are all very predatory journals, you know. This is not research, please remember. Conrad example, which we do in final year level or in MTech level in optimization. So you can teach this topology optimization in additive manufacturing course, in FEM course, and in optimization course. These are those courses which I lecture, और तीनों में ये करवाता हूँ as a project. Okay, so this is no great research, but there are these some articles in Congress of Mechanical Design, ये हल्के फुल्के जर्नलों में छपा हुआ है. You can see it. Right, let me show you an example which we did. This is a fashionable plaster, isn't it? And as you can see, this is used for wrist. So wrist cast, this is one of my MTech student, Mohammad Ahad Islam. He did it in 2020 and we went on to patent it also, and it's a granted patent. So what we did was we made for a wrist fracture. So your wrists often get fractured. The moment you land, suddenly you put your hand. Naturally, we tend to put our hand and your wrists get fractured. And the conventional way of plastering it is using that chunawala white thing, the heavy one, the itchy one. So that was the motivation of the work, and I have it here in front of me. I can show it to you. This is 3D printed, and those holes are all topology optimized and in PLA material with the Velcro. So if I put my wrist here, it will be acting like a cast. Although, well, doctors still rely on that. However, we start off with reverse engineering or scanning of my wrist. So the patient who has the fracture can be quickly scanned. It's hardly 10 minutes job. And once you have the point cloud, as you know, in reverse engineering, you get point clouds, millions of points you get. Those points can be fitted into surfaces, and those surfaces can be then printed using 3D printer. Like there, you can print it. You can also, before this, do what is called topology optimization. So taking those holes out, you see. Now what I said, topology optimization, focus on holes. Some of the holes are big, some of the holes are in different shape. Their location is all different, their size is all different. So size, number, and location of holes is nothing but topology optimization. And that's what we did here. You put it in your this thing. The advantage is, you know, these holes, ye jo holes rehte hain, this can breathe. Whereas if you recall your cast, after 1 week, it becomes itchy. And then it is heavy also. It is very, very rigid type. You don't need that rigidity. You need rigidity in this area, no doubt, so that it is mobile. But ये इस area में क्या करना है? इसके क्या role है? यहाँ कोई load नहीं आना. The only load has to come around where the wrist area, which has to be stiff and rigid. So that was one. So yes, we are going towards the end and the demo. Any ideas are clicking, by the way? Where can you use it? So please write it in the chat box. Where can you possibly apply topology optimization using additive in your research or in your projects, in your student projects? Yeah. So this is that last thing. कामयाबी की प्रतीक्षा ना करें, जाकर हासिल खुद करें. Even the tiger or the lion have to struggle very hard for grabbing the meal. Likewise for you. All right, those are our areas where we can potentially collaborate on finite element and reverse engineering and CAD and 3D printing, some optimization using MATLAB, polymer composite, design of experiments using Minitab. So anybody who is interested can potentially write to me. You're most welcome. Right, so this is that. After that, we'll see a demo of Abacus finite element. Yes, let me put my hands in respect and regard to the team at UCR who have this AICT, and obviously my funders at the Motilal Nehru at Allahabad and the University of Johannesburg, where I have worked, and the Queen's University in Belfast, UK, where also I have worked. Right, let's see the finite element demo. The software I'll use is called Abacus. Now, as you know, in finite element, there are 3 blocks. First block is called pre-processing. Second is analysis. Third is post-processing. It's like a recipe making. You're cooking biryani. When you cook biryani, you don't straight away put the fire or the gas, you don't turn on. So all those ingredients which you need in terms of spices or rice and piyaj and whatnot, that is all called pre-processing. Once that is ready, only then you do the actual cooking. And once the recipe is ready, you can taste it and tell that how many marks it is. 7.5 out of 10. Was it good on top, less on top? So something like that is finite element. Now in Abacus, these 3 is like this. So we will begin with part modeling. I'll show you, demonstrate. Just bear with me for another 2 minutes and I'll demonstrate next 15 minutes. So for what we do is the CAD modeling. As you know, your structure has to be there. So the CAD model of that will be there. We will assign what is called materials. The material properties, for example, modulus of elasticity and Poisson's ratio, we will assign. Then we will do analysis is called step. Whether you want to do static analysis or dynamic analysis or frequency analysis or heat transfer analysis, all that is covered in this something called step. Interaction is contact. So we'll do only one part, so no contact, but friction, etc. can be defined in contact. Load, UDL, point load, moment load, all you can define, and boundary conditions can be also defined. Pinned joint, hinged joint, fixed joint, etc. can be. Meshing, as you know, is the heart. Meshing, as you know, is the heart of finite element. So type of mesh, the type of element, the order, whether it's a linear or a quadratic, what size of element are you choosing, all these options. I'm sure plenty of you are aware of finite element. You might have done somewhere or the other, 1D problem, 2D problem, 3D problem. The choice is yours. Using ANSYS or Abacus, I'm demonstrating with Abacus. So all this green up to there is nothing but pre-processing. Abhi optimization ki kuch baat nahi ki, but please remember we'll define task. Task means we'll say pick topology optimize. Response, your response is variables. Strain energy is one variable, volume fraction is another variable. Objective function, strain energy to be minimized. And constraint is volume fraction, say 40 or 50 or 30. This we will define. So this is also an input for optimization. Agar optimization nahi karna hai, normal static analysis, you don't do optimization. And then this red is nothing but the solution, the second phase. Once the solution is nice and good, you are happy with the results, you can do what is called visualization. Graphs dekh sakte, tables dekh sakte, etc. Yeah. So what I'll do is I'll move over to Abacus. Okay. Is it visible, Dr. Wayne?
Yes, sir. Yes,
Yes,
sir.
sir,
Visible.
it's visible.
Okay, okay. So you see, this is how Abacus is decked up. You see part, property, step, load, mesh, optimization, job, visualization. So let's begin with part, you see. So this is that example I'll show you of, yeah. So you remember this example I showed you? याद आ रहा होगा ना? एक ऐसा triangular bracket था. Let me rotate it.
Yes, sir. Yes, sir.
Yes,
याद
sir.
आ रहा होगा ऐसा?
Yes, sir.
Where what I had done was I had applied load on the top there, UDL. I will show it to you also, and boundary conditions. So this is that original part. Okay. So let's go to property. Property is there, edit it, I'll show it to you. So Young's modulus I have defined as 200 GPa and the Poisson's ratio is 0.3. Please remember this is static analysis. Very, very easy. Okay. So we'll come to step. Let me show you in step. As I said, the step is static general. So static analysis. What can we do in step? The type of analysis, dynamic analysis karna. तो यहाँ पे चुनते हैं आप. Okay, we are doing static analysis, and then we come to let me show you the next thing, which is load. So for example, load I'll show you here. I'll edit it. So this is the on top surface. I have put a load, which is which type of load? You see that pressure is the load. The value is 10. Okay, don't worry about the units. Don't worry about the magnitude. Just focus on the concept, basic. So that is my load, and then I will rotate it and show it to you here. Yeah, rotate it there. Yes, and then I'll show you the boundary condition. This is the boundary condition manager. I'll click it and show you this. So when you will see this, this is the boundary condition. What is the boundary condition? You see, it's called Ncaster. Ncaster means fixed. Fixed में क्या होता है? The 6 degrees of freedom at a point are curtailed or controlled. So the 3 displacements in XYZ and the 3 rotations along XYZ axis are all curtailed. You all know basic stendo materials. What's the fixed beam, what is the overhang, what's the simply support. If I want to pin it, I can pin it there. If I want to fix it, etc. So this is boundary condition. What did we start with? Part, property, step, load, mesh. Let's see mesh now. So that's my mesh there. I can just zoom it a bit. Have a look, ladies and gentlemen. This is a TET mesh because the problem is 3D. Had it been 2D, we could have worked with triangles. This is 3D, so the mesh is TET mesh. Although this is a very fine mesh here. So what? Please remember, low stress area से वो खाना शुरू कर दे. जैसे पिज्जा में होता है ना कि बड़ा सा पिज्जा, उसके फिर आपने 20 पार्ट कर लिए, फिर एक खा लिया तो दूसरा शेप आया, फिर 2 खा लेंगे तो दूसरा शेप बचेगा. Something like that is going to happen. So this is my mesh. And optimization also I'll show you right away. Let me show you this. As I said, this is the type of optimization. So if you click here, you see click here, it will say topology, shape, size. We are doing topology. Okay, already done. Because please remember, it takes a while. This is a 3D problem. It could take 35 minutes, 45 minutes. So I've already solved it and I'll show you the result. Second problem is the responses. What were the 2 responses? Strain energy and volume fraction. So let me show you. You see this strain energy and volume. This is another problem where weight is also there. We will use only strain energy and volume. Okay. And then I see the third one, which is called objective function. So the objective function is this design response one, which was strain energy. Usko minimize karna problem. Okay. And the fourth, last thing which is there is called constraint. So what is the constraint? Let's see the third response dynamic, the design response is called volume fraction. Our target is 40%. So start with 100, bring down to 40. It means reduce by 60. So that is there. I have already solved it. I'll show you the results of, first I'll show you the results of static FEA. Why static FEA? To get a trend of this test. कहाँ ज़्यादा कहाँ कम पहले पता तो लगे. So let's see it. Okay, this is von Mises here, which you see on top. And then I'll show a stress plot. Yeah. So let me rotate it. Let me rotate it. Yeah. ये देखिए, ladies and gentlemen, you can see what it's a clear indication that this stress is 10 MPa and this stress is 142. So that green and white, and please also remember, I have frozen, I showed you that I have frozen the top area. There will be no biting, no element will be reduced. So this is that area where maximum material will be removed, and from here you will go this way, this way, this way, this way. ऐसा कट करके वो एकदम बाइट करता हुआ आगे चला जाएगा. Let me show you the optimization results also. I have already made it ready, not this one. Yes. So I will show you. So this is my original shape. You see this? So here I have reduced the element density slightly. There were a lot of tet elements here, but just for the sake of quick solution, I have reduced the number of elements. So this is my original thing, and now what I will do is start. You see, ये देखिए. So you at the bottom you will see cycles. This is second cycle, third cycle, fourth cycle, fifth cycle, sixth cycle. Can you see, ladies and gentlemen, slowly the material is getting reduced? Can you see? Hello?
Yes, sir. Yes, sir.
दिख रहा है ना? तो ये आपको हमने स्ट्रेस का ट्रेंड दिखाया. I showed you the stress trend. On the left side, it was minimum. Blue area was minimum. It is not disturbing the top area. So you see, I will go on doing the bottom. At the bottom, you can see currently I have 20 cycles. So this is iteration. Topology optimization is going on and on and on until it will touch 40%. I think 40 or 30 कितना था याद नहीं आ रहा. 40. Can you see? This is the last cycle पे यहाँ पहुँच गया. I will rotate it and show it to you. You see, अंदर तक खा गया. दिख रहा है? अंदर तक हटा दिया है. If you can see, अंदर तक सारा elements हटा दिया है. From the front, it is like this, but it doesn't matter what is in the front. You also need total volume. So you started with 100 and you came down to 60. Almost 40% is बड़ा बड़ा area अंदर भी गया. So this is that example of one of those topology. Let me quickly show you another example, which is from another example. Quickly, I'll show you cantilever. Yes. So this is another example. This is a 2D example, ladies and gentlemen. The previous example was a 3D. So here, if you see, this is like a plane stress problem. I'm sure you know what is plane stress and plane strain. This is a plane stress problem. Okay. So the front view is there. I'll quickly show you the I think, okay, let me not go to the load and boundary condition. Let me directly show you the results part of it. Okay, 732 already. Yeah, visualization. So I'll cover this. Yes. And the other one is this. Yes. So if you can see, this is that original object. Yeah, ऐसा. इसमें क्या किया था? I had applied the load here. It's like a cantilever beam with a point load at that right side, and the fixity is here. So what will happen is I will start optimizing it. You will see, and you will end up finally with a shape. Just a minute. Yeah, you will end up with a shape. Yeah. So this is that shape. You can see how the shape is converting over cycles. At the bottom, you see 14 cycles. So you initially started with a rectangle, but please see the shape now. every iteration it is becoming more stiffer and stiffer and stiffer and stiffer. अभी मैं ये स्ट्रेस दिखा रहा हूं इसलिए ऐसे दिख रहा है. आई शुड बेटर शो यू मैट प्रॉप नॉर्मलाइज. मैट प्रॉप नॉर्मलाइज क्या याद है आपको? 1 और 0 के बीच में है. 1 मीन्स फुल, रेड मीन्स फुल सॉलिड. लेट्स गो बैक अगेन. सो आई विल स्टार्ट ऑफ विथ, यू विल स्टार्ट सीइंग मैट प्रॉप नॉर्मलाइज का शेप. देखिए जो लाल लाल है ये कनेक्टिविटी बन रही है. Can you see? So instead of having that full rectangle like cantilever, इसकी जगह you will have a 40% lightweight, 60% depending on the problem, and you will get a shape like this. That's your final thing. You start off with zoom मुझे disturb यहाँ कर रहा. Okay, you start off with this. ये दिख रहा है, देखिए. You start off with this. If I show you, there was the load, this left end was fixed, and that's your last shape. So I have superimposed original. The original is blue, the remaining is red. बात समझ में आ रही है? अगर मैं हटा दूं उसको ओरिजिनल को तो ये लाल, ये शेप बच रहा है. And please remember, it will not fail. So ladies and gentlemen, this was a quick demo of abacus also. I think, yeah, time is already 7:34. Let me stop sharing. And I'll be more than happy to take any questions. Yeah, thank you.
Thank you so much, sir. For our audience, any doubt or questions, your side you can ask.
Any doubts? How many participants? 91.
Hello, sir. Good evening, sir.
Hi, Dr. Sharma. Yeah.
Sir, is there any software available in which we can control the different shapes which we can use for printing different parts? Because we have 3D printing softwares now, which I have, in which I am unable to control the different shapes, so which we can check the strength of complete part.
Yeah. See, as I said, SolidWorks also has topology optimization. ANSYS has it. Abacus has it. वहां पे आप करिए. अब आप, I think you are asking कि कैसे करके कैसे, how will you process it? So
Yes, sir, because ना I saw that different you show के आपने जैसे अभी दिखाया ना था कि हम क्या कहते हैं कि अगर क्वाड है या हेक्स एलिमेंट जैसे होते हैं, तो उस केस में हम अगर डिफरेंट अपना कोई एक डिफरेंट टाइप का स्ट्रक्चर क्रिएट करें इन बिटवीन, वो पूरा पैटर्न फॉलो हो जाए शेप में, और फिर हम उसको डिफरेंट लोडिंग कंडीशन टेस्ट कर सके, तो वो डिफरेंट जो हमारी ग्रिड्स बनती है ना, उसको हम किसी डिफरेंट सॉफ्टवेयर कंट्रोल कर सकते हैं.
Oh, okay. That is finite element. So you have to go to finite element software. By the way, SolidWorks has finite element. ANSYS has finite element. You can do a bit of CAD modeling everywhere. You can do a bit of FEM everywhere. So to get topology optimization, please remember that topology optimization, which I told you, is all finite element based. And you need meshing, load, boundary condition. ये क्या है? ये classical FEM है. Okay. So start with, you go to YouTube, pick any software. So SolidWorks for your students and all, you can pick it. अब होगा क्या कि आप बनाएंगे प्रॉब्लम. देयर आर लॉट ऑफ एग्जांपल्स. एक सी क्लिप का एग्जांपल है, यू मे नोट इट. सी क्लिप का, तो सी क्लिप पहले ऐसी सी शेप की होती है और फिर उसके बाद वो बहुत ही लाइट वेट बनती है. ओके, दिस यू कैन प्रिंट इट. अब टेस्टिंग कैसे करना है, आप क्या करिए, रियल लाइफ में आप बनाइए कि कैंटिलीवर बीम पे पॉइंट लोड WL3/3AI आपको पता है, और फिर उसके बाद उस पे लगा दीजिए लोड और मेजर कर लीजिए उस डिफ्लेक्शन को. इफ यू आर somehow able to measure the deflection, you will find the same deflection. जबकि material you will use only 40%. Instead of 100, you will use 40, whereas the deflection will be the same. Yeah.
Okay, sir.
And for more, you can write to me. My email ID is already shared with you.
Sure, sure. Thank you, sir. Thank you.
Thank you. Any questions?
Sir, some questions in chat box.
Please read them out.
How IoT be utilized for optimization in Industry 4.0?
IoT is a sensor-based thing. You see, this is Internet of Things. It's all sensor-based. So sensors are only useful in collecting data, whether it is pressure, temperature, humidity, or whatever, deflection. Those are coming as data. Now, how to use in topology optimization? Maybe to apply loads. For example, I am saying that this is put, say on this I put something like, say here. Now, how much a load is coming or how much deflection is coming, I have to monitor it. So that is where IoT can be used for sensor data. Yeah. Humidity, temperature, any variable can be measured nowadays. Yeah. Any other? Mute hand, Dr. Naveed. You're muted.
Okay, sir. Okay. Sorry,
Yeah.
sir.
Yeah.
What are the challenges in certifying topology optimized parts for automotive aerospace application?
Oh, very good example. Very good question. Yes. As I said, you see, nice and good it looks, but ultimately it has to be manufactured. And then that manufactured thing has to be tested. You can test again using finite element virtually. And then that is where it will be certified. And finally, in aerospace and automobile, everything has to be certified. Just a chassis. Say, take a simple example of a chassis. As of now, the chassis might be overweight, over designed, isn't it? जैसे बाटा का जूता है ओवर डिजाइंड है सो यू विल स्टार्ट मेकिंग इट लाइट वेट एंड लाइट वेट वंस इट बिकम्स लाइट वेट यू कैन डू अ फाइनल FEM of the lightweight structure and see the distribution of stresses, and those stresses should not exceed. So please remember, in trying to make it lightweight, it should not exceed the factor of safety, or it should not go below it, or should not be overstressed. Yeah.
Okay. Thank you so much, sir. Any doubts? Okay. Thank you so much, sir. I am honored to extend a heartfelt vote thanks to our esteemed resource person, Professor Mukul Shukla, sir, for gracing this session within presence and for delivering a insightful and enrichment talk regarding to Industry 4.0 to Industry 4. Industry 6.0. Very knowledgeable this session. His deep expertise, scholarly clarity, and practical perspective have grateful benefits for all participants and added immense value to today's program. On behalf of the organizer, faculty members, and participants, I express our sincere gratitude to Professor Shukla sir for taking their time to share his extensive knowledge and experience with us. His contribution has truly elevated to academic qualities of this event. We also thankful our attendees for their active participation during the expert talk, which ensured the success of this session. Once again, our grateful thanks to Professor Shukla sir for his exceptional engagement and for inspiring us with his profound insight. Thank you so much, sir, for
Thank you, Dr.
giving
Naveen,
your
for hosting me. And good luck to all the participants. Let the journey continue of academics. बढ़िया बढ़िया काम करिए तभी होगा. देखिए स्टूडेंट पढ़ने को तैयार नहीं है आजकल.
जी,
Everything
जी.
is available on the internet and YouTube. Wonderful videos. Why would one listen to you? Huh? They're not already seeing any books, etc. So it's a big challenge for we teachers. So you need to upgrade and skill yourself. Only then the survival will be there. My good luck with you all. Peace.
Thank you so much. Good night, sir.
Thank you.
Thank you so much, sir.
Okay, all the best. Bye-bye.
Moving ahead, it's my distinct honor to introduce second eminent resource person for the day, Mr. Kesles Srivastava, sir. Mr. Kesles Srivastava is highly experienced and engineering professional. One minute. Mr. Kisla Srivastava is a highly experienced engineering professional with over 16 years of extensive expertise in boiler technology, thermal power plant operation, and water treatment plant management. He is presently serving as an executive engineer in the electricity generation department of Uttar Pradesh Raj Vidyut Utpadan Nigam Limited UP RVNL as a reputed semi-public sector organization under the government of Uttar Pradesh. Throughout his distinct career, Mr. Srivastava has been closely associated with critical operation areas of thermal power generation, including boiler performance optimization, water quality management, safety compliance, and process efficiency enhancement. His technical competence combined with his strong analytical abilities and practical field experience contribute significantly to the reliable and sustainable operation of power plants generation units. Sir, based in Lucknow, Uttar Pradesh, Mr. Srivastava continues to play a pivotal role in the state of energy sectors. His professional journey reflects dedication, leadership, and a commitment to continuous learning, making him an valuable contributor to capacity building and industry academia initiatives. Now invite our respected resource person to expert talk for the today's session. Kesle sir, please
Hello, good
open
evening.
the. Uh, yes, sir, please, please on the camera. Yes, sir. Thank you so much, sir. Yes, sir.
Good evening, all
Very good honest.
participants. Thank you, Mr. Yadav, and all the faculty members of UCR.
Yes.
Are you getting my voice?
Yes, yes, sir. Getting.
Is it clear?
Yes, sir. Yes, sir. Clear. Please share, sir, your PPTs.
Share. Okay. Can I start?
Yes, sir. Yes, sir.
So,
Sir, please F5 for full screen of PPT. Please F5. Press F5.
this is okay?
No, sir. In sir, below the screen, we have one option for increasing the percentage of slide. Just left side, one option is for the full screen.
Audio, video, participants, chat.
No, sir. No, sir. In the
More.
PPT. In the PPT.
Just a minute.
Sir, please continue. No issue. Please continue, sir.
Okay.
Sir,
Now
yes,
it
sir.
is-
Visible. Yes, sir. Full screen. Please
Thank you
continue.
for Actually, my topic is smart and sustainable solutions for water and sewage treatment. Basically, I am coming from Obra thermal power plant, and I will discuss the. All of you know the scarcity of the water. We should not waste the water, and water is one of the most precious resource on the earth. All of you know, all must be protected not only as habitat for countless organisms, but also for its critical role in industrial process and all the as vital resource of our life. Today, I will discuss first the DM plant. So, DM plant means demineralization plant. In thermal power generation, WTP, what means water treatment plant, where we are producing DM water, demineralized water, एंड इट इज वेरी सीरियस मैटर. जैसे आप समझते हैं कि हमारा ब्लड बिल्कुल प्योर होना चाहिए बॉडी के लिए, समझ रहे हैं आप लोग? तो उसी तरीके से हमारे पावर प्लांट का जो ब्लड है वो डीएम वाटर है. अगर वो उसके पीएच थोड़ा सा भी डिस्टर्ब होता है तो बॉयलर में ट्यूब लीकेजेस शुरू हो जाते हैं. ऑल ऑफ यू गेटिंग माय पॉइंट?
Yes, sir. Yes, sir.
ओके, तो मैं ये आपको बताना चाहता हूँ कि ये जो डीएम प्लांट है इसमें बेसिकली हम पीएच को मॉनिटर करते हैं मेनली. और हम पीएच को, अगर आप पीएच केमिस्ट्री में पढ़े हो तो उसमें पावर ऑफ हाइड्रोजन आयन कंसंट्रेशन मींस पीएच। हाइड्रोजन आयन की कंसंट्रेशन कितनी है इस वाटर में, उस पीएच को हम सिस्टम में मॉनिटर करते हैं। ठीक है, जनरली 6.5 से 7.5 के बीच में होना चाहिए। जो हम डीएम वाटर प्रोड्यूस करते हैं डब्ल्यूटीपी में, मींस वाटर ट्रीटमेंट प्लांट में, वो हम बॉयलर के लिए 6.5 से 7.5 के बीच में होना चाहिए। ऑल ऑफ यू गेटिंग माय पॉइंट?
Yes, sir. Please continue,
अच्छा,
sir.
आपके दिमाग में या एक जनरल क्वेश्चन हो सकता है कि डीएम वाटर है, वो भी बॉयलर में जाना है, तो उसको हम 7 क्यों नहीं रखते हैं, न्यूट्रल पीएच? अगर 7 है उसका मतलब वो पीएच स्केल में 7 है, तो इज न्यूट्रल बिहेवियर, ना ही वो एसिडिक है ना ही वो बेसिक है। जितना 7 से वैल्यू कम होती है, आप सभी को पता होगा कि वो एसिडिक करेक्टर शो करता है। So, water treatment plants in thermal plant purifies water to prevent scaling, corrosion, damage to boilers and turbines also. ये मैं इसको और ऐड कर रहा हूँ कि बॉयलर के लिए नहीं, ये टरबाइन के लिए भी बहुत ज्यादा जो है घातक है, जिसे कहते हैं। आप समझ गए कि अगर हम डीएम वाटर की जो प्रोसेस है, जो मेकिंग है, अगर हमने इसको मॉनिटर नहीं किया तो वंस अगर वो बॉयलर में एंटर कर गया तो वो बॉयलर के साथ साथ टरबाइन के ब्लेड्स को भी अफेक्ट करता है। तो मेरी पोस्टिंग वहां पर थी डब्ल्यूटीपी में। बीइंग ए मैकेनिकल इंजीनियर, आई वाज वेरी कंसर्न अबाउट द केमिस्ट्री एज वेल एज बॉयलर हेल्थ। तो मेरी पोस्टिंग वहां पे रही है, और मैंने वहां पर जो प्रोसेस रीड किए केमिस्ट के साथ, क्योंकि केमिस्ट की वहाँ पोस्टिंग होती थी जनरली, मैं वहां पर असिस्टेंट इंजीनियर था। तो मैं आपको ये प्रोसेस थोड़ा सा विजुलाइज करने की कोशिश करूंगा। आप लोग को पता है क्लैरिफिकेशन क्या होता है, या क्लैरिफिकेटर क्या होता है, किसी को पता है? चलिए ठीक है, मैं आपको एक स्कीम बताता हूँ कि वो रॉ वाटर, जो बिल्कुल रॉ वाटर मीन्स उसमें हमने कोई भी डोजिंग नहीं की है, रॉ वाटर को हम क्लैरिफिकेटर में सबसे पहले एंटर करवाते हैं। क्लैरिफिकेटर एक तरह का, आप कभी अपने देखा होगा कि इनिशियल जो स्लजेस होते हैं उसको एक ब्रिज के थ्रू रोटेट करता हुआ पार्ट है, वो उसको जो है क्लैरिफिकेशन करता है। और मैं इसको स्लाइड में भी दिखा सकता हूँ। ये
ताली ताली
so basically clarificator works. Its key process include pre-treatment to remove suspended solids and demineralize the initial sediments, or you can say it screens the heavy particles and of water, and it goes through clarificator through degasifier. Now, degasifier cleans the uh, dissolves oxygen. Mr. Rakesh, are you listening me? Dr. Rakesh,
Yes, sir. हाँ.
can you It is, I think,
सर जो
some problem.
व्हाट्सएप पे पीपीटी है, सर व्हाट्सएप पे जो पीपीटी है उसको डाउनलोड करके उसको शेयर करिए सर।
अच्छा, जस्ट a minute.
हाँ ये
Sorry
वाली
for.
हटा दीजिए।
ओके सर, कोई नहीं, प्लीज।
Okay.
परेशान कर लिया बेटा, हमको परेशान कर लिया, हमको गुस्सा आ रहा है, कह इसको पार्क जाओ, इसको इसको अकेले जाओगी तो आगे।
ये डॉक्टर राकेश, ये जो शेयर का ऑप्शन आ रहा है इसमें,
ओके सर, शेयर दिस पीपीटी इन दिस साइड।
ओके, कैन यू शेयर?
वो सर, वन वन 1 मिनट।
ओके. यस.
ये सर, प्लीज कंटिन्यू सर।
ये जो पिक्चर में आप देख रहे हैं, एक ब्रिज. यस, यस. इस पिक्चर में आप ध्यान से अगर देखें तो बीच के जो सर्किल है इसमें वाटर कलेक्ट है. आप लोग देख रहे हैं, ऑल ऑफ यू. तो इसमें वाटर, इनिशियली रॉ वाटर यहाँ पर इस पोर्शन पे आता है, और ये ब्रिज जो है रोटेट करता है. एक तरह से आप कभी अगर आप इसको कहें हिंदी भाषा में, मथनी का रोल करता है. कि इनिशियली ये क्या करता है, सेडिमेंट्स को, रॉ वाटर के सेडिमेंट्स को डिस्पोज करके नीचे की तरफ कलेक्ट करता है, और यहाँ से आउटर बाउंड्री से ये जो पानी है वो हमारे डीएम प्लांट में जाता है. ये इनिशियल स्क्रीनिंग होती है, समझ रहे हैं तो. और सेडिमेंट्स अपना जो है सेटल हो जाते हैं नीचे की तरफ, और फिर वो, ये जो पोर्शन दिख रहा है आपको यहाँ पे, यहाँ से होते हुए वो अपना सेटल होते जाते हैं. अब हमारा जो ये वाटर है, जो क्लैरिफाइड वाटर है जिसे कहते हैं, वो जाता है डीगैसीफायर में. डीगैसीफायर का रोल आप ये समझिए, जो डिजॉल्व ऑक्सीजन है वो हमारे लिए प्रॉब्लम कर सकती है, तो उसमें से CO2 और O2 दोनों को, गैसेस को क्या करता है डीगैसीफायर, रिमूव करता है. और रिमूव करते ही वो आपका जो डीगैसिफाइड वाटर है आपके प्रेशर फिल्टर्स में जाता है, और प्रेशर फिल्टर्स से होते हुए वहां पर मेनली 7 प्रेशर फिल्टर्स होते हैं, डिपेंडिंग अपॉन द रिक्वायरमेंट ऑफ द वाटर. ओके. एंड ये जो आपका डीगैसिफायर से होते हुए प्रेशर फिल्टर में पानी गया है, वो दो तरह के एक्सचेंजर्स में जाता है, नेमली कैटायन एक्सचेंजर और एनायन एक्सचेंजर. आप सभी को पता होगा केमिस्ट्री में, एनायन एक्सचेंजर में एनायंस एक्सचेंज होते हैं. वाटर के अंदर जो भी प्रेजेंट एनायंस प्रेजेंट हैं वो एनायन एक्सचेंजर में एनायन एक्सचेंज होते हैं. और एक्सचेंजर्स टिपिकली एक सिलिंड्रिकल शेप का वेसल होता है, उसमें रेजिन्स होती हैं, और रेजिन्स अपना रोल करती हैं कि अगर मान लीजिए कि वो एनायन एक्सचेंजर में पानी गया फर्स्टली, तो उससे जितने भी एनायन एक्सचेंज हुए वो कैटायन एक्सचेंज में के लिए प्रोसीड कर जाता है. फर्स्टली एनायन एक्सचेंजर में जाता है एंड देन कैटायन एक्सचेंज में वो पानी जाता है, और इस तरह से होते हुए डीमिनरलाइज वाटर जो है हमारा बन जाता है। अब इसकी इसकी मॉनिटरिंग टोटली जो है मैनुअल होती है वहां पे, क्योंकि ओबरा बहुत पुराना प्लांट है। बेसिकली अब हम लोग जो बात कर रहे हैं स्मार्ट और सस्टेनेबल सोल्यूशन की, तो स्मार्ट मीन्स आप सभी से लोग समझ रहे हैं कि स्मार्ट का मतलब ये हुआ कि हमारी मॉनिटरिंग बहुत स्मार्टली हो, बहुत ज्यादा मैनुअल डिपेंडेंसी ना हो। तो हर सेलियंट पॉइंट्स पे हमारे चीनोमीटर या इंस्ट्रूमेंट्स लगे होते हैं, जिससे कि वो उस पॉइंट पर पीएच टर्बिडिटी हम लोग जो है आराम से उसको मॉनिटर करते रहते हैं। और सेलियंट पॉइंट्स पे अगर हमें ऐसा लगता है तो वहीं पर हम लोग अपने प्रोसेस को रिपीट करवा देते हैं बैक फ्लैश के थ्रू, या जो भी हमारा कलेक्टर है उसके पास जाता है। अब आपका जो डीएम वाटर है वो रेडी है बॉयलर में जाने के लिए। अदर वाटर ट्रीटमेंट्स में अगर हम बात करें, कूलिंग वाटर ट्रीटमेंट, वाटर इज यूज्ड इन द cooling towers treated with chemicals like scaling and corrosion inhibitors to prevent buildup and degradation of equipment. Basically, we are very much aware about the damages. We should avoid damages of boiler tubes and as well as turbine blades, because it will affect the generation of the electricity as well as life of boiler and turbine blades also. So after this circuit, wastewater treatment after use, wastewater is remove pollutants like heavy metals and suspended solids before it discharge in order to comply environmental regulations. Basically इस समय जो प्रेजेंट सिनेरियो है, अगर हम बात करें तो हम केमिकल डोजिंग्स या जो भी कर रहे हैं डीएम वाटर जनरेट करने के लिए, वो ऐसा नहीं है कि हम कास्टिक सोडा या जो भी एनायन एक्सचेंजर में डाल रहे हैं वो फ्रीली आप डाल सकते हो या डोज कर सकते हो। उसकी एक सर्टेन लिमिट्स है कि अगर हमने उसको एक्सेस लिमिट में अगर आपने डोज कर दिया तो एनजीटी आपने सुना होगा, नेशनल ग्रीन ट्रिब्यूनल, वो हम लोग पर पेनाल्टी भी इम्पोज कर सकता है। और कर सकता है क्या, एनजीटी की तरफ तो क्लियर कट गाइडलाइंस है कि आप इतनी ही डोजिंग करेंगे, इतना ही वाटर में इतनी ही डोजिंग करेंगे, प्लस इतना ही ट्रीट करते हुए केमिकल्स को हम आगे जो है फ्यूचर के लिए या और भी ज्यादा रॉ वाटर के लिए यूज करेंगे। आर यू गेटिंग माय पॉइंट?
Yes, sir. Yes, sir.
तो बेसिकली दिमाग में कोई पिक्चर बन रही है, मतलब ऐसा मैं, अगर उसकी फोटोग्राफ्स अलाउड नहीं होती है बेसिकली प्लांट में, फोटोग्राफी अलाउड नहीं होती है, क्योंकि डॉक्टर राकेश ने कहा था कि कोई फोटो तो होगी तो सर शेयर करिएगा।
पैसा देना
वो सीआईएसएफ, अगर आप लोग इंडस्ट्रियल विजिट करेंगे तो मैं आपको दिखा सकता हूँ, वो तो परमिशन होती है सीजीएल की, लेकिन बेसिकली मैं फोटो शेयर नहीं कर सकता बीइंग ए गवर्नमेंट एम्प्लॉय या बीइंग ए, यू कैन सी, ये हमारे पास रेस्ट्रिक्शंस है। तो हम उसकी इमेज को हम ऐसे ही शेयर कर सकते हैं। और कैन यू प्रोसीड दिस साइड टू दैट साइड?
हमारी चाबी हमको दे देना।
यस, नेक्स्ट।
और कार्ड दे देना।
Now advanced, sorry please pull back, advanced oxidation, एडवांस ऑक्सीडेशन प्रोसेस में आपका यूवी प्लस H2O2 जिसे आप कहते हैं हाइड्रोजन पेरोक्साइड, और ओजोन ट्रीटमेंट भी हम लोग करने लगे हैं टू किल द कंटेमिनेशन ऑफ द वाटर। बेसिकली हम क्या कर रहे हैं, हम वाटर को इतना ज्यादा कंटेमिनेशन फ्री कर रहे हैं या स्लज फ्री कर रहे हैं कि हम आगे जो भी एनायन एक्सचेंजर या कैटायन एक्सचेंजर्स वहां पे इंस्टॉल है वो डैमेज ना करें, क्योंकि हम लोग इतने माइक्रो लेवल पे एनालिसिस करते हैं। तो अब आजकल जो की फीचर है वो एडवांस ऑक्सीडेशन का फीचर है। बहुत पहले ये यूज नहीं होता था। इट इज ए मॉडर्न टेक्निक, एडवांस्ड ऑक्सीडेशन प्रोसेस, जिसको आप एओपीज कहते हैं। इसमें आप यूवी मेथड भी यूज करते हैं और प्लस इसमें ही हाइड्रोजन पेरोक्साइड की भी डोजिंग करते हैं। ओके, नाउ लो एनर्जी desalination if needed, forward osmosis process or membrane distillation. We are not using this technique. Okay, solar power pumping and disinfection. सोलर पावर पे आप लोग बहुत ज्यादा हम लोग की अभी एक्सप्लोर नहीं किया है, आप लोगों ने स्विच नहीं किया है। ठीक है, नेक्स्ट स्लाइड। यस, ऑटोमेशन एंड डिजिटल मॉनिटरिंग। अगर आप किसी भी डीएम प्लांट को ले लें या किसी भी प्लांट को ले लें, अगर आपके पास रियल टाइम डाटा नहीं है तो आप हर जगह लैग करेंगे। ये आपको समझ में आ रहा होगा। अगर हमने चाहे केमिकल डोजिंग की हो, चाहे फॉस्फेट डोजिंग की हो या डीगैसीफायर में, तो हमारे पास रियल टाइम मॉनिटरिंग होनी चाहिए। एक टर्म है टर्बिडिटी, ऑल ऑफ यू नो टर्बिडिटी। टर्बिडिटी मीन्स बहुत ज्यादा, जैसे एक ग्लास में बहुत क्लीन वाटर लीजिए, आरओ वाटर लीजिए, और एक आप ऐसे ही किसी नल से आप टैप से पानी लीजिए, तो वो थोड़ा सा टर्बिड होगा क्योंकि वो क्लीन तो है नहीं। तो आरओ वाटर बिल्कुल क्लीन वाटर है, और उसके रिलेटिवली जो आपने डायरेक्ट किसी टैप से कलेक्ट किया है, तो उसको एज्यूम करेंगे तो मोर टर्बिडिटी मीन्स मोर सेडिमेंट्स। ओके, तो इलेक्ट्रिसिटी यूज फॉर इलेक्ट्रिसिटी जनरेशन इज ऑल्सो है प्रिंसिपल कंसर्न फॉर आवर प्लांट्स। तो अगर हम लोगों ने ज्यादा इलेक्ट्रिसिटी, मोटर्स को नहीं हम लोगों ने किया मॉनिटर कि वो ज्यादा करंट ले रहा है, बहुत ज्यादा कम एफिशिएंट है, तो उसको भी हम लोग मॉनिटर करते हैं, क्योंकि ये सब डायरेक्ट इफेक्ट करता है कि ऑक्सिलरी पावर कंजप्शन का। प्लांट्स में ऑक्सिलरी पावर कंजप्शन रीडिंग आती है कि कोई भी प्लांट कितना ज्यादा इलेक्ट्रिसिटी यूज कर रहा है। तो उसको मॉनिटर करते हुए हम लोगों ने हर जगह सिस्टम लगाए हैं। स्काडा सिस्टम भी है हमारे यहाँ, और अब तो और भी अच्छे अच्छे एनटीपीसी वगैरह तो और हेल्दी सिस्टम यूज कर रहे हैं। वी आर अचीविंग दैट टेक्नोलॉजी। तो प्रिडिक्टिव मेंटेनेंस, जैसा कि आप लोगों ने मैकेनिकल इंजीनियर्स जानते होंगे कि हम प्रिडिक्ट कर लें उस मेंटेनेंस को, कि जो मेंटेनेंस होने की पॉसिबिलिटी है। तो प्रिडिक्टिव मेंटेनेंस यूजिंग सेंसर्स टू डिटेक्ट पंप वाइब्रेशन, मोटर टेम्परेचर एंड प्रेशर वेरिएशंस reduces breakdowns of associated auxiliaries। ये वाटर ट्रीटमेंट प्लांट की जो भी एसोसिएटेड ऑक्सिलरीज हैं, अगर पंप में वाइब्रेशन है वो भी डिटेक्ट कर लेता है। मोटर में भी अगर टेम्परेचर, मोटर का वाइंडिंग टेम्परेचर अगर बेसिकली हम लोग देख रहे हैं, लगातार फील कर रहे हैं कि हाँ ये मोटर आज नहीं तो कल जो है इसकी कॉइल डैमेज हो सकती है, तो ये प्रेडिक्टिव मेंटेनेंस में आता है। और हम लोग जो है उसको क्या करते हैं, स्टैंड बाई मोटर को सर्विस में ले लेते हैं, और फिर इलेक्ट्रिकल डिपार्टमेंट को बोलते हैं कि आप इस मोटर को रिप्लेस करिए या जो भी प्रॉब्लम है सॉर्ट आउट करिए। आजकल एक ट्रेंड है एआई, आर्टिफिशियल बेस्ड प्रोसेस ऑप्टिमाइजेशन। तो एआई को भी हम लोग इनकर कर रहे हैं, लेकिन हम लोग के ओबरा प्लांट में अभी एआई, अभी हम लोगों ने इसको अडॉप्ट नहीं कर पाए हैं ड्यू टू सम लैक्सिटी और यू कैन से गवर्नमेंट ऑर्डर्स। तो एआई बेस्ड प्रोसेस ऑप्टिमाइजेशन टू एडजस्ट एरेशन, केमिकल डोजिंग एंड स्लज हैंडलिंग ऑटोमेटिकली। बेसिकली अभी हम लोग क्या करते हैं, मैनुअली वेल्व से केमिकल डोजिंग करते हैं, या एरेशन को, मान लीजिए डीगैसीफायर का वॉल्व है, जितना मान लीजिए टू रिवॉल्व करना है, इसको खोलना है, ओपन करना है, तो वो मैनुअल में कुछ ज्यादा ही ऑपरेटर ने इसको खोल दिया। तो एआई बेस्ड प्रोसेस अगर हम लोग यूज करेंगे, तो जितना वाल्व की ओपनिंग करनी है, क्लोजिंग करनी है, वो बिल्कुल एग्जैक्ट होगी। उससे भी बहुत ज्यादा पावर कंजप्शन घटेगा और ब्रेकडाउन भी घटेंगे। अल्टीमेटली हमारी ऑक्सीजन को भी हमें सेव करना है जो वाटर ट्रीटमेंट प्लांट में लगी हुई है। स्मार्ट लीड डिटेक्शन, हमारे प्लांट में हमने जो पाया था, क्योंकि वो बहुत पुराना प्लांट था, कि लीकेजेस बहुत होते थे। तो लीकेजेस को मैनुअली हम लोग ने देखा, या हमारे ऑपरेटर ने या हमारे केमिस्ट ने बताया, और हम लोगों ने टीम भेजी मेंटेनेंस डिपार्टमेंट की कि इसको जो है लीकेजेस को आप थोड़ा सा ट्रेस करिए, अगर हो सके तो उसको ऑनलाइन ही कर दीजिए, क्योंकि एक बार प्लांट बंद करने का मतलब है कि डीएम वाटर को हम क्या कर रहे हैं, प्रोडक्शन को अफेक्ट कर रहे हैं। तो स्मार्ट लीक डिटेक्शन लगे हुए हैं, प्रेशर फिल्टर भी लगे हुए हैं, प्रेशर मीटर भी लगे हुए हैं कि कहाँ तक प्रेशर कितना था। मान लीजिए 1 एटमॉस्फेयर प्रेशर था, वो गिर के 0.9 हो गया किसी पाइपलाइन पे, इसका मतलब कहीं ना कहीं लीकेज है। तो स्मार्ट लीक डिटेक्शन टेक्नोलॉजी हम लोग यूज करना शुरू कर दिए हैं। अभी हम लोग उस तक उस लेवल की टेक्नोलॉजी यूज नहीं कर पाए हैं, एनटीपीसी वैसे अडॉप्ट कर रहा है। नेक्स्ट, सीवेज ट्रीटमेंट प्लांट। अभी मैंने आपको डिस्कस भी किया कि स्कैर्सिटी ऑफ वाटर इज ए चैलेंज, ठीक है। तो सीवेज ट्रीटमेंट प्लांट में भी सिमिलर वर्क होता है कि इनिशियली जो है, जो सीवेज वाटर है किसी कंटेनर में आता है, और उससे क्या होता है, हम वहां पर क्लैरिफिकेटर नहीं होता है, वहां पर बेसिकली इनिशियल सेडिमेंट स्क्रीन्स लगी होती हैं, स्क्रीन से वाटर पास होता है और इनिशियल सेडिमेंट्स जो है क्लियर होते हैं। टर्बो ब्लोअर्स वहां पे लगे होते हैं। ब्लोअर्स आप सभी समझ रहे हैं कि ब्लोअर्स का काम वही है जो डीगैसिफायर का है, कि हम वाटर के गैसेस को हम रिमूव कर सकें। डिफ्यूज्ड एरेशन विथ डीओ बेस्ड कंट्रोल एंड वेरिएबल फ्रीक्वेंसी ड्राइव्स, वीएफडीज कहते हैं इसको, बाद में डिस्कस करते हैं। नाउ, एनारोबिक डाइजेशन फॉर स्लज जनरेट्स बायोगैस फॉर इलेक्ट्रिसिटी और हीट। अब ये आपका एक प्रॉफिट जनरेशन अगर आपका है, तो आपने जो आपकी जो इसके बाय प्रोडक्ट्स हैं, जिसमें बायोगैस भी आ रहा है और इलेक्ट्रिसिटी भी जनरेट कर रहे हैं, ठीक है। कंस्ट्रक्टेड वेटलैंड्स, लो कॉस्ट नेचर बेस्ड पॉलिशिंग। नेक्स्ट, ये फिर से देखिए, क्लैरिफिकेटर का एक और पिक्चर मैंने शेयर किया है, इसमें भी आपको एक ब्रिज दिखाई दे रहा है सेंटर पे, ये ब्रिज है,
यस
और
सर।
बीच के जो सर्किल में वाटर कलेक्ट हुआ, और फिर बाद में जैसे ही ये क्लियर होते होते क्या हुआ, सॉरी, बाहर से कलेक्ट होते होते ये अंदर आया, और ये जैसे ही इसने रोटेट किया, इनिशियल सेडिमेंट्स इसके क्या हुए, नीचे यहाँ पर सेटल होते होते नीचे एक तरह का सेडिमेंट एरिया है वो कलेक्ट हो जाता है। ये पिक्चर उतनी क्लियर नहीं है हालांकि, और ये भी किसी प्लांट से अनऑथराइज्ड वे में शायद कैप्चर की गई है। नेक्स्ट, अब ये चैलेंज हमारा जो है, स्मार्ट एंड सस्टेनेबल सॉल्यूशन फॉर वाटर एज वेल एज सीवेज ट्रीटमेंट प्लांट। तो एनर्जी एफिशिएंट ट्रीटमेंट टेक्नोलॉजी हम यूज कर रहे हैं, और हम हर ऑक्सिलरी में को मॉनिटर कर रहे हैं कि इसमें अगर रिक्वायर्ड वैल्यू से ज्यादा वो एनर्जी कंज्यूम कर रही है तो हम उसको चेक करें। प्री चेकिंग तो पॉसिबल नहीं है, जब हमारा प्लांट रन कर जाता है तभी तो हम देख सकते हैं कि हाँ, कहाँ कहाँ पर किस सैलिएंट पॉइंट्स पे या कौन सी ऑक्सिलरी ज्यादा इलेक्ट्रिसिटी कंज्यूम कर रही है, क्योंकि मैंने आपको बताया कि इसका डायरेक्ट इफेक्ट क्या किस पे है, ऑक्सिलरी कंजम्पशन पे है। और जब भी किसी भी थर्मल पावर प्लांट की बात होती है, तो हमें आउटपुट तो दिखता है कि 200 मेगावाट या 200 मेगावाट का बॉयलर है, दैट मीन्स 200 मेगावाट वो इलेक्ट्रिसिटी जनरेट कर रहा होगा, लेकिन वो इस जनरेशन में कितना इलेक्ट्रिसिटी कंज्यूम कर रहा है, वो बहुत बड़ा चैलेंज है। और इस समय एनर्जी मॉनिटर करना, एनर्जी को और एफिशिएंट वे में टेक्नोलॉजी को यूज करना, ये हमारे लिए चैलेंज भी है, और हमारे पास ऐसे ऐसे सॉफ्टवेयर हैं जिससे हम प्रेडिक्ट कर लेते हैं कि कहाँ पे ये इस तरह के लॉसेस हो सकते हैं या हो रहे हैं। नेक्स्ट, मैंने जैसा बताया कि एडवांस ऑक्सीडेशन प्रोसेस, ये इसमें अल्ट्रावायलेट यूवी और H2O2 मतलब हाइड्रोजन पेरोक्साइड का ही ट्रीटमेंट होता है, फॉर डिफिकल्ट कंटेमिनेशन के लिए हम यूज करते हैं। डिफिकल्ट मीन्स ऐसे जिद्दी दाग, जैसे एरियल का ऐड आता है कि कंटेमिनेशन को हमें क्लियर करना है, उसके लिए हम एओपीज का यूज करते हैं, एडवांस्ड ऑक्सीडेशन प्रोसेसेस। लो एनर्जी डिसेलेरेशन इफ नीडेड। ये भी रिवर्स ऑस्मोसिस आपने सुना होगा। अब फॉरवर्ड ऑस्मोसिस को भी हम वर्क कर रहे हैं। मेम्ब्रेन डिस्टिलेशन। ओके। सोलर पावर्ड पंपिंग एंड डिस इन्फेक्शन। अब हम सोलर पे जब स्विच कर रहे हैं तो हम क्यों ना हो कि ऑक्सिलरी पावर को कंजम्पशन को कम करने के लिए सोलर पावर का यूज कर लें अपनी ऑक्सिलरीज को रन करने के लिए। समझ में आ रही बात? तो हम सोलर पावर को यूज करते हैं डिफरेंट ऑक्सिलरीज को चलाने के लिए। और जनरली अब ये मैंडेटरी भी हो जाएगा हर घरों के लिए भी कि आप कुछ इलेक्ट्रिसिटी जनरेट भी करिए और वो क्या करिए, ग्रिड में दीजिए। इससे क्या होगा, आपके बिल का लोड भी कम होगा और आप भी कंट्रीब्यूट करेंगे जनरेशन के लिए। नेक्स्ट। डॉक्टर राकेश, आर यू लिसनिंग माय
Yes,
वॉइस?
sir. Yes, sir. Yes, sir.
यस।
Sir, please
एरेशन
continue.
ऑप्टिमाइजेशन। यस। Now I am discussing about the aeration optimization. Optimization, all of you know the technique which can optimize the whole process. So turbo blowers are using, we are using turbo blowers. Blowers, as you know, जैसे डीगैसिफायर मैंने बताया था, वाटर ट्रीटमेंट प्लांट होते हैं, तो टर्बो ब्लोअर्स का हम यूज करते हैं कि टू एक्सट्रैक्ट द डिजॉल्व गैसेस इन द वाटर। डिफ्यूज एरेशन विथ डीओ बेस्ड कंट्रोल, variable frequency drives, anaerobic digestion for such. Generate biogas. It generates biogas for electricity or heat. Can power 30 to 80% of plant energy needs. तो जो भी प्लांट की एनर्जी रिक्वायरमेंट है 30 to 80% तक, वो हम क्या कर लेते हैं, बायोगैस इलेक्ट्रिसिटी से भी हम मेकअप कर सकते हैं। कंस्ट्रक्टेड वेटलैंड्स, लो कॉस्ट नेचर बेस्ड पॉलिशिंग। एक वीडियो था राकेश जी, अगर
Yes. Sir, there is no video.
हाँ, तो पहले ये डिस्कस कर
Please,
लें।
sir. Sir, please continue from PPT.
ओके। ओके। अभी आपको जो मैंने ये वाटर ट्रीटमेंट प्लांट बताया, बेसिकली ओबरा का, इसमें वाटर जो भी हम प्योरीफाई कर रहे हैं या डीएम वाटर बना रहे हैं, उसको हमें रीयूज भी करना है। बिकॉज एनजीटी इज मॉनिटरिंग, कॉन्टिन्यूसली मॉनिटरिंग द वेस्टेज। ओके। एनजीटी मीन्स नेशनल ग्रीन ट्रिब्यूनल। वो लगातार मॉनिटर करता है कि अगर आपने कोई भी अप्रोच गलत की तो वो सीधे सीधे पेनाल्टी हमारे प्लांट्स पे लगाता है, इम्पोज कर देता है। और ये नॉन चैलेंजेबल होता है, ये नहीं सोचिए कि आप इसको चैलेंज कर सकते हैं। वो अपने रडार से या जो भी है इनका जो सिस्टम है मॉनिटर करने का, बेसिकली ये लोग आई थिंक उससे भी करते हैं। आपका क्या कहते हैं, जैसे नहीं स्पेस में जो लगा हुआ है इसको, तो खैर ये मतलब एनजीटी अपना ये लगातार मॉनिटर कर रहा है। तो अगर हम एसटीपी के यूज करेंगे, ट्रीटेड वाटर्स रीयूज फॉर इरिगेशन, हम इरिगेशन के लिए यूज कर सकते हैं। अगर हम थर्मल प्लांट की बात करें तो कूलिंग टावर्स में भी हम इसको भेज देते हैं, जो रीयूज कर सकते हैं हम। इंडस्ट्रियल प्रोसेसेस के लिए भी भेज सकते हैं। एक आजकल बहुत ही स्मार्ट तरीका है टॉयलेट फ्लशिंग के लिए। हम क्यों, जो आपका मतलब एक तरह का ड्रिंकिंग या ड्रिंकिंग वाटर है या फ्रेश वाटर है, हम टॉयलेट में क्यों फ्लश करें। हम इसी तरह के वाटर जो यूज हो चुका है, जो हमारे लिए अब किसी भी काम का नहीं है, उसको टॉयलेट फ्लशिंग में कर सकते हैं। ग्राउंड वाटर रिचार्ज, आप सभी जान रहे हैं कि बारिश अब कम हो रही है, तो ग्राउंड वाटर को भी रिचार्ज करना बहुत जरूरी है। वो किसी रीजन के लिए है, ऐसा नहीं कि सभी रीजन में हम ग्राउंड वाटर को रिचार्ज करें। न्यूट्रिएंट रिकवरी, फॉस्फोरस एज स्टेटिव एंड नाइट्रोजन फॉर फर्टिलाइजर्स। आप सभी जानते हैं कि फर्टिलाइजर्स में मेनली नाइट्रोजन का ही रोल है। ओके, अगर हम वाटर यूज की बात WT की भी करें तो WTP के लिए भी, तो वेस्ट टू रिसोर्स फ्रॉम फिल्टर बैक वॉश, वाटर रिसाइकलिंग, एनर्जी रिकवरी फ्रॉम प्रेशर इन डिस्ट्रीब्यूशन नेटवर्क्स। बैक वॉश का मतलब अगर पैरामीटर नहीं आया है, किसी भी वाटर को अगर हमने भेजा है और पीएच सेटिस्फाई नहीं है, तो हम उसको बैक वॉशिंग भी करते हैं। और होपफुली अगर आप लोगों को इंडस्ट्रियल विजिट कराई जाए तो आप लोग WTP जाइएगा, तो वो ज्यादा विजुलाइज होगा। और अभी एक वीडियो भी डॉक्टर यादव आपको शेयर करेंगे, मतलब इस स्लाइड में मैंने वो किया है। नेक्स्ट। यस, रिन्यूएबल एनर्जी इंटीग्रेशन, solar panels on reservoirs, plant roofs or over canals. Next, biogas for sludge digester to power blowers or generators. और स्मॉल हाइड्रो टर्बाइंस जो कैप्टिव पावर प्लांट्स हैं, वो भी स्मॉल हाइड्रो टर्बाइंस के लिए भी हम रिन्यूएबल एनर्जी को इंटीग्रेट कर सकते हैं। तो इसका रिजल्ट क्या होगा? मोस्ट प्लांट टुवर्ड्स नेट जीरो एनर्जी ऑपरेशंस। हम कोई भी बिना इनपुट दिए अगर हमको एनर्जी मिल रही है तो ये बहुत बड़ी बात है। नेक्स्ट। जस्ट जैसे मैंने कहा था कि जो बेसिकली हम डोजिंग करते थे केमिकल्स की WTP में, वो मैनुअली करते थे। अब ये स्मार्ट डोजिंग सिस्टम विथ ऑनलाइन एनालाइजर यूजिंग AI टू रिड्यूस कोएगुलेंट यूजेज। बेसिकली अगर आपको इसको समझना है तो स्मार्ट डोजिंग, हमने जो भी फीड कर दिया, मान लीजिए सोडियम फॉस्फेट ही है, फॉस्फेट डोजिंग कर रहे हैं कि अगर 50 ml पर लीटर ही डोज करना है तो 50 ml से 1 ml भी ज्यादा डोज नहीं करेगा। तो हम स्मार्ट डोजर्स बेसिकली जो भी वहां पर लगाए जाते हैं, इंस्टॉल किए जाते हैं, उसमें हम लोग इनपुट देते हैं, वो उतनी ही, जैसे कॉफी मशीन होती है, आपने 50 ml ही प्रेस किया तो 50 ml ही वो आउटपुट देगी। तो इस तरह से हम केमिकल्स को सेव करते हैं। मैनुअली ऑपरेटर से पढ़े लिखे नहीं होते हैं, उनको बोला कि जाओ ओपन कर दो वॉल को, केमिकल डोजिंग करनी है, तो वो महाराज गए और उन्होंने जो है, मतलब सम लैक्सिटी, मतलब इंटेंसली उन्होंने नहीं किया, लेकिन क्या है कि हमने स्मार्ट डोजिंग सिस्टम को अडॉप्ट किया नहीं था, तो वो उसकी गलती नहीं है। मेम्ब्रेन फिल्ट्रेशन, आप समझते हैं कि एक्सचेंजर्स के अंदर मेम्ब्रेन्स होती हैं। जैसे आपके यहाँ RO वाटर्स बेसिकली हर घरों में होगा, तो उसकी मेम्ब्रेन्स क्या होती है, दिन पे दिन, डे बाय डे डिटोरेट होती जाती है, उसके ऊपर स्लज जमा होना शुरू हो जाता है। तो उसके लिए भी हम लोग को मेंटेनेंस कराना पड़ता है। तो हम इतना ज्यादा क्लीन वाटर एक्सचेंजर में भेजें कि मेम्ब्रेन्स जो है हेल्दी रहे लॉन्ग टर्म के लिए, वो ये मैं बताना चाहता हूँ। एक्टिवेटेड कार्बन भी आप समझ रहे हैं कि वो एक तरह से कार्बन के जो पिलेट्स है, वो जो भी है, उसको एब्जॉर्ब कर ले रहे हैं सेडिमेंट्स को। इससे भी एक्सचेंजर्स की लाइफ बहुत ज्यादा बढ़ रही है। नेक्स्ट। अब इसका नेचर बेस्ड सॉल्यूशंस, ग्रीन बफर्स अराउंड प्लांट्स फॉर ओडर कंट्रोल एंड टेम्परेचर रिडक्शन। ओडर भी एक बेसिकली, अगर आप सीवेज ट्रीटमेंट प्लांट्स के आसपास जाएं तो बहुत बैड ऑडर मतलब फील होती है, उसको भी अब हम लोग बेसिकली अरेस्ट करने के लिए इस तरह से ग्रीन बफर्स और ये सब यूज कर रहे हैं। और केमिकल्स भी ऐसे स्मार्ट केमिकल्स आ रहे हैं कि वो जैसे ऑर्डर को क्लिक करके वो वाटर को एक अप टू द पैरामीटर प्रोड्यूस करेगा। फ्लोटिंग वेटलैंड्स इन ट्रीटेड वाटर्स, इको फ्रेंडली सर्च ड्राइंग बेड्स विद प्लांटेड वेटलैंड्स। ऐसा वेटलैंड्स हम प्रोड्यूस करें जिससे कि हम प्लांटेशन कर सकें, क्योंकि प्लांट्स को भी अगर बहुत, मतलब एक तरह से वाटर न्यूट्रिएंट है, अगर खराब पानी मिला तो वो ग्रो नहीं कर पाएगा। नेक्स्ट। लो कार्बन इंफ्रास्ट्रक्चर, use sustainable materials, modular construction, and efficient pumps, oblique blowers. Heat recovery from wastewater streams for buildings or process heating. Next, smart management and community integration. Digital twins for plant simulation and optimization. Demand forecasting for water usage. Public dashboards for transparency and conservation awareness.
Thank you, sir, for
Uh,
excellent session for the different types of problems related to the power plants. Thank you. So,
these are challenges.
yes, sir, challenges during the power plants. Any questions from the audience side? Please ask. Any doubts? Okay, sir.
It's okay, sir. It's okay.
Okay.
Thank you very much, sir, for your insightful and enriching session. On behalf of the Department of Mechanical Engineering, UCR, and the Atal AICT FDP organizing team, I extend our sincere gratitude to Mr. Kisle Srivastava, sir, for sharing his valuable knowledge
Okay.
and expertise with us today. Your session has greatly enhanced understanding and added significantly value to this program. We are truly honored to have you with us. Thank you once again, sir, for giving your valuable times and very important factors related to the power plants are sharing, sir. Thank you so much, sir.
Okay. Thank you, audience.
All participants, please check your chat box for the feedback form. Thank you so much, sir. Good night, sir. Hmm. 15 minutes time for the feedback session. All participants, please fill the feedback form.